I gave you one, but yeah, I see a
Oh,
second
okay.
one. And there's 4 people waiting.
Yeah, good times.
Yeah.
Everybody's waiting. I did post on the Vince Story Discord that I was going to start streaming this with a link. So hopefully some
Ah.
people can stop by and say hi and kind of be involved in the production of a mod here. So starting the stream here, and yeah, I'm looking forward to seeing everybody. And if anybody has any questions about modding in general or about this project, let me know. Um, and I will try to address whatever I can. Some things I'm woefully ignorant of, and some things that we can look at together and figure out. So, yeah. So what I'm working on is the electrical network system for the Vintage Engineering mod, and I've got the catenary, i.e., the wire set up here. So all of these objects, I know my picture is in the way, but all of these is part of the catenary system. And I used for sort of the basis. I used the support beam system, and I call the support beam like uh, procedures to generate it, but I use the built-in slump per meter, and I just for the wires to go in between 2 points. So the catenary system is more or less ready to be tested and ready to be fleshed out. I haven't really tested any of this code yet, which is really scary because this is a lot of code. But yeah, so the catenary system is basically as far as I can get it without testing it. So I moved on to the electrical network system because the catenary system doesn't do anything on its own. You need a system on top of that to actually make use of it. And so therefore we are making the electrical network system. So this is where we're at today. We are going to try to finish the meat and potatoes of the entire system here, which is the update tick for the electrical network, right? So the hierarchy is relatively simple. Simple in theory. Can be a little bit complicated in practice because on the top layer you have the catenary system, and the catenary system is named such because it can be any type of wire. You can run any kind of wire. It's moddable. You can add your own types of wire to it. Not a big deal, right? So the catenary system does not create or care about any network. All it is for, is running wires. And the wires are, in this case, just a block that it generates the mesh of, right? So just like the support beam is a block, the wire from A to B is a block. And that's the catenary system that runs that. It does not care about what networks are associated with it. All it cares about is can you run a wire from A to B? And I've got all the objects set up to have the callbacks in order to do that. So, how do you make the network? Well, the layer under that, right, is the electrical network mod. And let's see, let me bring that up. So the electrical network mod is the actual mod, right? This is a mod system. Basically, every system in the game is a mod system. The game is built on the modding API. So everything in the game, your hunger system, crop growth, the weather, all of those are all mod systems. If you look in your log file when you start the game, there's just a list of mod systems that the game loads, and that's what this is. It's just a mod system, like all of the other ones. It is a server-side only mod, so this will only need to be run on the server because the client does not care about the electrical networks. The client can run wires. That's the catenary mod, not the electrical network. So this is strictly a server-side only mod. Only the server manages saves, loads, and updates the electrical network. The client does not care about it. Okay, so you have the electrical network mod, right? The mod has a manager, and the manager is really where a lot of work is going to need to be done. I don't have nearly this object done yet or testable, but the electrical network manager, let's bring that up. Electrical network manager. Okay, so the manager, all of its tracking are all the networks that you have, right? So the electrical network manager has a master dictionary, which is a key value pairing. The key being the network ID and the value being the electrical network itself. So you have you have just the manager, all of its storing is all of the different networks. That's all that it's doing is managing and maintaining all of the networks. And so you have initializing the manager, and you have the game tick with the manager, right? So one of the things I'm doing here is trying to model the base game. I'm trying to model a vintage story as much as I can with all of this objects. This is a lot for me to chew on. But when this thing loads and then I initialize it, I'm grabbing the two main events, right? So the catenary mod, when a wire connection is made, you take a wire and you right-click this node, drag it over, and you right-click that node. First thing it does is verify that you can actually connect it to the node. So there's a node connection verification. But if that all passes and the connection is made, it fires an event. And the event fires and says, hey, I just connected this wire, the wire that I'm holding, so it passes the wire to this spot, to this spot. And it just fires that event and then forgets about it, right? It doesn't care. All it does is fire that event. Well, I need to pick that event up, right? So I could have 20 different mods that are all building a network. Well, if I have a mod that's telephone network, well, it would be trying to find the communication wire variant, and it would ignore the power variant. So it's up to the mod author to pick up and consume the events that they need. So this grabs the event and says, hey, I want to be notified when there's a connection made or one disconnected. I want to be notified. Now, I don't have either of those procedures done, right? So there's even an exception there to really tell me that those aren't done. But this is where all of your logic is going to go in. And to figure out, there's going to be a lot of logic. These two procedures are going to be nasty pieces of work. Because when you have a wire connected, right? When wire is meant from A to B, then I need to figure out, is it part of a network? Is it extending a network? Is it a brand new network? If it's extending a network, is it connecting two different networks? This is where all of the logic goes in terms of what I'm connecting. So you need the first step is to verify the wire type that you're using is the proper version, right? So you've got all of the different power, LV, MV, HV, EV, whatever. So you've got all the different powers, and then you have to verify that the wire type is the right one. And if it is, then you're going into saying, okay, you're past the start node and end node. So now you need to analyze the start node and figure out all of the connections there. And it's a mountain of code that's going to go into each one of those. And that is I'm going to have to do that offline because that's going to be a lot of the head banging on the desk. A lot of that. It's going to be a lot of that. But anyway, assuming these are good to go, if the connection is made, then it's, you're passing then data into the network system. And so the individual network is a more or less very simple thing. Okay. And the network itself is just a collection of nodes. That's all it is. I'm thinking of like Minecraft and some of the crazy networks that exist there. Consider like the applied energistic system. So an AE system is a network. And then the cables and wires, those are all nodes on that network. An interface, a pattern provider, an export bus, an import bus. Those are all nodes on the network. And so you start to understand why channels were introduced in the case of AE to limit the number of nodes on an individual network. Because when you start getting lots of nodes, it's hard for the network to update itself. It's hard for the network to tick itself, right? You have to update all of those nodes all of the time, and I understand why networks have to be limited, which is where our MV and LV system comes. It's going to limit like how much power you're going to be able to push on a network, and you may only get 4 machines available on a network because it's just not enough power. So it's kind of built in to limit the size of networks a little bit, which is fine. Okay, so the network, then we're going to come in here, and then we have an add node, we have a remove node. Some of these I'm actually working on. I'm kind of, from this angle, I'm working from the bottom up, trying to figure out, well, if we're just going to get added a node, that's pretty straightforward, right? Just add a node to this network. That's pretty easy to do. So, as you can see, there's a little bit more to it than that, because here's the all nodes one, right? This is getting into today's stream, the switch statement here. So what I did, as I was working on all day yesterday, what I'm thinking of is, all right, imagine the network gets an update tick, and I take care of that in the network manager, in the on tick, the update tick, right? So on game tick, this is right here called by this. So I register a game tick listener with the API for every 250 milliseconds, right? So every quarter of a second, this is going to tick while I come in here and I say, hey, for every network that we have, update it. This is what this does. If we don't have any networks return because, maybe early game, when you first load the game, the mod exists, but you don't have any networks. So why do too much? So if there are no networks, just bounce out. But if we do have networks, whether it's 1 or 50, iterate through each one of them and update it. The update tick is what I'm going for here. And if we come in here, the update tick is what we're going to be working on today. This, when I say the meat and potatoes, this update tick is the thing that distributes power in the network and called every quarter of a second. So all of our, the reason I also include delta time is you have to take whatever power per second variable exists in the machine or the generator or whatever, and you have to sort of scale it by delta time. So the update tick is where it all distributes. But I was running into a logical problem because one of the things that I need to do in the flow of this procedure is literally coming in and saying, how much power do we need? How much power do we have? And let's distribute that power. You know, and power that we need is coming from all of the machines. Power that we have is coming from generators as well as storage. And then figuring out all that. So, you know, if it's a tiny itty bitty network, you know, it's not going to take that long to iterate through all the objects. But you want to minimize the number of times you iterate through all of the objects in a list, right? Anybody who's taken, you know, beginners like computer programming course, one of the first things they teach you in the algorithm section is the different sorts, you know, the bubble sort, the heap sort, all the way up to the quick sort, right? The sorting algorithms are a really good way of just telling you how inefficient an algorithm is, right? And the efficiency of an algorithm is based on the number of times that it touches or looks at the elements of the array, right? So bubble sort is classified as an n-squared algorithm. You literally have to look at each element the number of times of every element. So if you have 1 million items to sort, say you have 1 million numbers or names or whatever, and you're trying to sort them with the bubble sort, it has to look at each item up to the number of items. So you're looking at you're trying to sort 1 million items. You could look at those items, each one of them 1 million times. It's an incredibly inefficient algorithm for large lists. Incredibly. It's really good for small itty bitty lists, but horrible for big lists. So that is what I have been rolling in the back of my mind. I want to make this as efficient as possible. And how do I do that? Well, my first attempt at this, way back last year, in the update tick, I took the main all nodes, right? So this is an all nodes. I grabbed all of the nodes, and then I basically organized them. I broke them out into consumers, producers, and storage. And once I had those 3 lists, then I would iterate through those. Now here's the problem when you're doing that in the update tick for every network. That is not an efficient thing to do. When you're taking a giant list and you're basically running a query on it with like LINQ, you're running a query on this list and saying, I only want producers. And it populate. You're basically running almost like a SQL query on the list. Doing that every tick is not a good thing to do. I knew going into it that it was bad, but I could see no other way of doing it. You know, on very, very small networks, let's say less than 10 nodes, you could theoretically just iterate through the thing and, you know, try to simulate it that way. It would be a mess to do that, though. It would be an utter mess. And that would be a special case. You don't want to have a special case because you want the update loop to apply to no matter what size the network. So, as you can see, I've got 3 other lists in this object: producer nodes, consumer nodes, and storage nodes, right? Those 3 other lists are added data points. So I have the all nodes, and then I have those other 3 nodes. Now, when I build those nodes, as you can see, they're actually lists of different types of objects. So all nodes is the iElectric node. That is a generic, very generic node type. The electric node here This is the iElectric node. Here is just the data that it has, position, the wire anchor that it's associated with, the power tier, and the entity type. Okay? So the entity type is producer, consumer, storage, transformer, toggle, whatever. So that's the entity type. This, more or less, comes out of this. So this is my test machine. And as you can see, entity type consumer, priority 5. Here's an index. Here's the power tier. So there's data involved. There's data points involved in the JSON that you can specify. And I want to move as much of this into JSON as possible. And so the wire nodes themselves are basically a cuboid. It's a box. It's just where is this wire node connection, right? So a little, you can have a little like voxel square on a machine, and that is where the wire will like visibly connect to. And when you look at it holding the wire, it will actually highlight it as a selection box. So a lot of this data is coming out of the JSON, and this is where my brain just, oh my god. So trying to keep all of this stuff straight is kind of a nightmare. But as you know, none of these objects actually allow you to interact with the power of the block itself, right? I can't, with all of these different blocks, I can't push power into them. None of the functions allow me to push power into them. I would have to, going back to the electrical network, if I just use this one, I would have to iterate through this and grab the position, because we know the block position. And once you have the block position, you can actually query the world and grab the entity at that position. So if I were to not have these, right, if these did not exist, I would have to iterate through this, grab all of the entities of all of those positions, and build the array that way. Again, that would be bad. If you have a network that's 100 machines on one network, that's 100 machines that it has to go and grab for every update tick. That is not cool. We do not want to do that, right? That is not a good idea. So when I was talking to Tyrone about this a few weeks ago, I told him, I was like, I am really trying to develop this mod with efficiency and with efficiency in mind to not drag down the game, right? I don't want to crush the simulation backend of the game. I've even thought of the update ticks scaling the tick rate of the thing, slowing down even more depending on how many networks. So when you start out and you've got maybe 5 networks, it's going to tick at a quarter of a second. But then if late game, if you got 25 networks, maybe then it ticks at every half a second. It's everything scales, but ticking it slower would help performance. And I have to get to a point to test all of that. But I digress. So I needed a way to grab this data and do it efficiently and not have to do it over and over and over again, because repeating it would be bad. So what I did is, you go into add node, so this is called when a node is added. I know, surprise, right? So this add node is called when the manager, the electric network manager, says, oh, they added a node to this network, and boom, it's fired to add node. The node is added, right? Now, we come in here and I say, hey, I want to grab the block entity at that position. I'm going to add the node. Here's the all node, right? This is adding the node by the position. So it's adding a new node to the list, or the dictionary, I should say. Let's be accurate. It's adding it to the dictionary, but at the same time, I grab the entity, right? So I'm grabbing the electrical block entity, and I make sure that it's not null, because it has to be the electrical block entity. It has to be that. And I use the interface because it could be Joe Bob's, electric generator, but it's the interface is what I'm after. It has to implement the interface, right? So if it doesn't, then I can't interact with it anyway. If it doesn't implement this interface, I don't know what procedures and functions it's going to have. So it has to do the interface. This is how Forge does it. We're going to take a look at my electrical block entity interface here in a second, but it's highly influenced by Forge's version of that same thing. I've got some of my own flavor added to it, but the electrical block entity, that is like how Forge Power works. It's one interface. That's it. That's how the Forge Power system works. Is just one interface. And all mod authors need to do is implement that interface. The same goes for here. Once this mod is released, if you want to build your own electrical machine, all you need is that interface. Right? There's this interface, and there's a couple of things you need to support for the catenary mod to verify a wire can be attached. And that's it. You add your own, machine to the mod, and it just loads because it's this interface. But the node position, the iElectric node, that has a position in it. So I just grab world accessor, get block entity at the position, and if it's null, obviously throw an exception, because it shouldn't be null. If we're adding the node, it should have already done that check. This is just a second sanity check. If something happened between verifying the wire can connect to now, it should be good to go. So add the node to the all nodes. Doesn't matter which order that is. Just add it. This all nodes is the thing that's going to be saved to disk. I'm going to be saving all of these networks to disk to avoid what happens with other networks in the game, where they're just rebuilt every time they're loaded. Every time they're loaded, they're rebuilt. And I don't want to do that for obvious reasons. So in here, I have a switch, and a switch is, if you're not familiar with a switch, it's just a way of doing a cascading if, if, else if, else if, else if, else if. It's just a way of doing that that's easier to read. So a switch on the electrical entity type, because now I'm accessing the iElectrical block entity. And so let's look at that. This is the meat and potatoes of how to interface with an electric block. All of my machines, all of the generators, transformers, storage, toggles, all of the things are going to have the iElectrical block entity. And it's a block entity. It's not a block. It is not a behavior. It is a block entity that you need to apply this to. Okay, so obviously we have max power, current power, the entity type, again, coming from the same place right here, right? The entity type is, even though I have it in multiple interfaces, it's going to be drawing from the same place. It's going to be drawing from that node right there, which is the block JSON attributes. Can receive power, can extract power, is powerful. These are just simple like procedures that you need to implement that we can that are part of the interface, so I know that they exist. Priority, this is my own little added feature. There's I think only one mod that I know of that you can set priorities on power, and that's the Flux Networks mod. In this one, the priority is on the network. So obviously, higher priority generators are first to empty, and machines are first to fill, right? So priority matters. Now, if everything is priority 5 or priority 10 or whatever it is, if they're all the same priority, then it doesn't matter what they are. But you can set priority, and I plan on supporting the ability to set priority in the GUI in some way, shape, or form. I don't know yet. Again, that is going to be figured out maybe later. I don't know. I don't know yet. But all of these codes you can see when you mouse over. You can see all of this coming up with the tooltip. So I've really tried to focus on documentation for all of these interfaces and stuff, because I want to make sure that people know what's going on. Okay, so priority, and then receive power and extract power. These are the two main functions, right? And I sort of looked at Forge's version of this, and this again is largely taken from those. But what it looks like, the U-long, right? So that's an unsigned long, and all of my power based things are unsigned long. The amount of power, the max value of an unsigned long is enormous. If you want an idea of how much it is the value of, remember that Draconic battery? So Draconic Evolution, there was that big orb, right? There was that giant orb that you could build as a battery. Well, the topmost tier of that was something like 9 quintillion power. That is the value of the U-long, right? Or approaching is just an enormous amount of power. So I'm really trying to future-proof this. It's funny, in order to save this to disk, I have to convert it to a long, save it, bring it back in, and then convert it back to a U-long. So I'm really hoping I don't lose any data with that. But anyway, I'm not dealing with fractional energy. There's no fractional energy. So it's not like 1.5 energy or 2 energy. So there are going to be rounding errors. And if you want to justify their existence, consider rounding errors the loss of heat, the loss in heat of power, right? Any electrical network anywhere in the world loses a percentage of its power via heat and resistance. So consider the rounding errors the realistic loss from resistance from power line. It's realistic. All right. So there is, it's funny, I don't actually have a block that implements this yet. I haven't even gone into my test generator and test machine to implement any of this stuff yet. I'm just now getting to the point where I'm able to do that. I wanted to wait to see what I needed. And there have been a few times now where I've added on or changed around some of these interfaces, especially like the electric node, right? Trying to figure out how best to figure all this stuff out. But it's a process. These are kind of growing organically as I'm going. Okay, so how this works is the way that I saw, or the way that I could discern how Forge does it, was a really clever way of doing it. And so I'm trying to I'm trying to get close to that. So as you can see, the return type is the same as the amount of power. So what happens is the machine receives power. So obviously this is a machine or a storage, right? A storage of some kind. So the machine is sent a value of how much power is being offered. Let's say I have a bank of power. And so I'm calling the machine to receive power, and I'm handing it all of my power. The machine takes all of that power, subtracts from it what it needs, and then returns what's left over. Then the next machine takes that value, subtracts what it wants, and returns what's left over. And you just do that in a loop, and it dwindles the amount of power down, and boom, it's gone. Right? It's either gone or there's a remainder that you don't need anymore. Now, the same can be true for the extract power, right? I want this much power. I want this much power. So you pass in how much power you want, which is a total. It gives a certain amount of power, which subtracts from its internal buffers. So it says, let's say it's a big network, and I want 5,000 power. Well, each machine is not going to have 5,000 power. So I want 5,000. So I hand in 5,000. The machine itself may say, well, I only have 200, I only have 500. I only have 500 power. So it's going to take that 5,000. It's going to remove 500 out of it. It's going to deplete its own reserves. And it's going to return 4,500. So now the next machine takes 4,500 and starts subtracting it, and may return 4,000. And you just iterate through, and eventually, after you get all the way down to the end, you either have power deficit or you have something available for like storage. And then the simulate, this is a flag that says this is a flag that says act as if this is the real deal, but don't actually change your internal buffers. Right? So you can iterate through as if it's real, and then you can be given a value, but not actually change the machine at all. And I'm not 100% sure what I would use that for. So if anybody has any idea of what use case that would be, because a lot of that data can be brought from here. Current power and max power. I'm not even sure if the Forge one had those on it. But these I can discern already for receive power, which is a machine. I can say what is the power differential here. Max power minus current power gives me how much power it needs. And I can iterate through and say, how much power do you need? And just using these two variables in the interface, I can figure out, I don't need to run the simulation. And the same with extract power, right? These are for generators or storage, and saying, well, current power and max power. Again, how much power do you have? And you can say if it's max power minus current power. Well, unfortunately, that doesn't give it to you right. You can just say current power. That's all you need for a generator. What is your current power? Because your current power is how much power you have offered, right? So you don't need, I don't even need to do any subtraction or anything. It's just how much power do you have, right? And so you can iterate through these pretty easily without actually running a procedure. You just grab those variables, which is just a memory address. Essentially, these will actually be maps. These are properties, not fields. Anyway, okay. So that's running this one down. So that is the interface that we have access to in this loop that we are going to work on. Right here. Okay. So getting back to our sorting, the sort discussion, where I think I've gone over this in my head many times, and I've discussed it with. I just talked out loud. I just kind of discussed it and tried to figure out the logics of it. But I think that I need to run through these lists at least twice. Now, if somebody can come up with a way, and hey, Thomas, greetings to you, sir. Greetings to you. If I iterate through these twice, that is basically a 2n algorithm, which isn't bad. There's not even a sort that is that simple. So a 2n would be fairly easy to pull off. Now, here's the other caveat to that. Networks will not very likely have generators and producers on the same network. Early game, they will. Obviously, early game, if you're looking at early game, a generator and you might even wire a generator directly up to a machine, right? There's no middleman. There's a network with one connection, and that is a machine to a generator. And that's it. And that's all the network is taking. And so there's one entry in producer and one entry in consumer. And that is a really dead easy thing to do, right? And you may get times when you start building your network that you have producers and consumers on the same network. But as soon as you start jumping into like higher tiers of power, like MV power, you're going to need transformers to support LV machines. You don't want to hook an MV network up to an LV machine. That is a bad idea. I may even prevent you from doing it altogether. So, mid-game, you're going to start separating your networks. So there's going to be a whole bunch of producers and no consumers. A whole bunch of consumers, but no producers. So in those cases, I've been thinking like, how the heck are you going to move power from A to B? Well, that's where transformers come in. Transformers are going to be a very special kind of storage, right? A storage just has one connection, right? But it can both take power and store and give power. So it's a special kind of machine. But a transformer is a special kind of storage where it has connections to more than one type of network, right? A transformer will have a connection to an MV and then a connection to, let's say, an LV. Well, those are going to be two separate networks. You have the MV side and then you have the LV side. Those are distinct networks. So it's a block. Imagine a square block. One wire is coming in here and another wire is going out there. There's two separate connections. One side is MV and the other side is LV. Those are two separate networks connected to the same block. So the transformer will have an internal buffer of power that you will be able to actually fill from either side. I went around and around on this. but you can actually fill it from either side. It's neutral. It's whatever side has a surplus of power. So if you're getting MV power from one end and there's an internal buffer, let's say there's enough buffer for 2 seconds of power in the transformer. 2 seconds. So let's say, again, as a example of how much power we're talking, let's say an LV network is limited to 512 power per second. The entire network, 512 power per second. Now let's say you have enough machines on that network to actually meet 512. Well, when you put another machine on that, now there's more machines on the network than you have power, and let's say you push on a little generator to make up the difference. Now you have that use case of, I have all these machines and then one little producer, one little generator on that network. So I'm getting power from the MV, which is trying to fill the buffer of the transformer. And I've got a generator on the other side as well. So, in programming, what we have to do a lot is run through all these edge use cases. Like, what would happen if, and you just set up a scenario in your mind, logically. You have a bunch of machines, and then you add a generator because you're running all of these machines and you're not enough power, so you add a generator. Now you're getting power from 2 different directions. Like, what's that going to look like? So basically, a transformer is just going to be a storage that can take power from either side, wherever there is a surplus, and basically move it along, right? So in that case, it works anyway, using the storage from either side, right? So either side can access the internal buffer of a transformer. It's just basically a battery that allows you to move power. So with that kind of solved in my head, I was able to go forward and go, okay, now that that's sort of solved and I know kind of how to handle that, now let's look at how do we actually figure this stuff out. So let's go down here and say we need a couple variables. Total power wanted. Total power given. Okay, I'm trying to logically do this. Don't expect clean code. Cleaning code comes after. The first rule of programming is get the damn thing to work, and then the second time you go through it, make it look cool, make it look clean. But the first time you go through, you just need to get it. You just need to give it. You just need to make it work. Total storage. Total storage. How about total in storage? Okay. Okay. So, ooh, look at that. Do you see that little pop? That was great. I love it. I love the IntelliSense. It's gotten so smart. It is actually scary how good it is now. It is scary how good the IntelliSense is nowadays. Okay, so total power wanted, total power given, total in storage. That is basically what we can grab from each one of these, right? And based on those numbers is how we handle this stuff. So total power wanted, which means we need to go through all of the consumer nodes. Okay, so we go through for each. I don't like using var. I hate when I see code and they have var. I hate it. I hate it. I hate it. Don't ever show me code. You need help on your mod and you're like, hey, I need some assistance. Can I send you some code or something? If I see var in there, I will immediately go, get that var out of there. Get it out. Because if you're just like leave it up to the compiler to what object type this is, that's the number one thing you want to get rid of. You want to specify what object it is. Ooh. Okay, so this is going to be electric block entity. Entity, not in all nodes. Nope, it's not in all nodes. It is in consumer nodes. Total power 1, consumer nodes. Okay. I know there's hotkeys for a lot of this. I just don't know what they are. So electrical block entity. So in consumer nodes, right, it is going to be an electrical block entity. It's the same type, right? Electrical block entity. So it's just going to be full of those. In the for each, it just iterates through them. Very, very nice, very handy. All of the generic types in C# are brilliant. They're just so brilliant. So this will iterate through, and I know total power wanted plus equals, because we're adding to it. Remember, we're adding to it. Total power wanted plus equals entity dot max power minus entity dot current power. So that very, very simple routine is adding, right? Is adding max power minus current power. This is how much power buffer is remaining in all the machines. Now remember, this is running every quarter of a second. So, the amount of power used in a quarter of a second, especially for the early game machines, is tiny. It's a tiny amount. So what we want is, whatever that little bit of, it might be 5 power, right? So it's not going to be a lot. It's not going to shut the machine down if we don't get power for 1 second. So total power wanted plus equals the power that we have remaining, right? Now, this might not even run because consumer nodes is empty, right? So, yeah. So now we want to do for each electrical block entity. Entity in producer nodes. You see how that came up? It was glorious. It just knew that I was going on to the producer nodes. Now we want total power given plus equals entity dot current power. Okay. Again, producers, whatever current power they have, we have. Maybe given is the wrong word. Offered. Okay. Total power wanted, total power offered. Now, we want for each electrical block entity in storage nodes. Oh, I love how that works. Total in storage. Hey, look at that. I told you. IntelliSense is insane in this app now. It is insane how it just knows what I want to do. It's crazy. It's crazy. So total in storage is how much we have in storage. Again, when I add a node, right? When I go through consumer type, add to consumer nodes. Producer type, add to producer nodes. Storage, storage cascades down to transformer, which adds it to storage. So both storage and transformer will add it to storage. That's kind of how that works. I don't have a break in there, so it goes to the next one and says, oh, we're going to do this. At least it did that before. Maybe they fixed it. I don't know. But as far as I know, cases cascade down if they don't have a break. So both storage and transformer should add to storage nodes. So transformers will be part of this. Now we have power that we want, power that is offered, and total in storage, which includes transformer. Now the tough part. Now what do we do? Now what do we do? And this is on the quiz. Now it's like, okay, we have the power that we want. We have the power we are. Now remember, I'm trying to minimize the number of times we iterate through all of it. I want to be able to do this with the minimum amount of shenanigans. Minimum. I want to iterate through them as least times as possible. Okay, so we have cases now. Let's say total power wanted compared to total power offered. Do we add the amount in storage to amount offered? That is because again, let's run through a scenario. This is how my mind works. I come up, I hit a wall like this. I'm like, all right, well, let's come up with this. Let's come up with a scenario. We have a network that's got 3 machines, and a transformer. Now there's 3 consumers and 1 storage. So we run through those machines and we're like, we need 25 power. There's obviously no producers, so the amount of offered is 0, but the amount in storage is the transformer, and let's say that's full. Let's say that's 1024. So we know we have 25 power. There's 1024 in the transformer. So in this case, yes, the amount of power offered needs to include that. But if the network also has a generator on it, then we have the generator power. I don't know. I talk myself into circles, and then I just convince myself. The other thing I do, I should note up here, when I add these electrical block entities to these consumer nodes, producer nodes, I immediately sort the list. I add it to the list, and then immediately I resort it based on priority. So they're already prioritized. So when we iterate through, we're already iterating by priority. I think. I hope. Maybe. Yeah, I hope. Void list sorts the elements in the list. Yeah, it should sort it. Now I could be way off because I've read different things that say the generic types like list. You don't know what order everything's going to be in. But I'm hoping that it works. If not, I'll have to change it to an array. But yeah, anyway. I will skip the ads. Thank you very much, YouTube. YouTube has gotten crazy. Okay, so if we want for total in storage to be total power offered, let's change this. U-long total power in gen. Total power in generator. equals total power in generator plus total in storage. Okay. So now I'm keeping these separated just because I don't know what logic what we're going to come up against, and I don't want to have to refactor a whole bunch of code. If we don't end up using it, then I can always clean it up later. But at this point, we now have variables for how much total power we want, how much total power is in the generators, how much total power is in storage, and how much total power is being offered by generators and storage. So this total power offered, right, we can come through and iterate. We now know how much power total that we have on offer. Now, here is total storage available. Okay. Okay. Again, I do. This is how I code. Total storage available. So we have the total power that's in the storage. But I also wanted how much power we have available in storage. You know, if all of the batteries or the transformer or whatever is like less than max power, then I need a way of storing how much power is available to push into them. Because there can be easily a network that is all transformers. Imagine that, right? So in that use case, if you think ahead into like the late game, oh my god, the amount of cat hair in my keyboard is kind of astounding. What is my cat chat online while I'm asleep or something? So you have a late game network where you have on one side you have a whole bunch of generators. Let's say you've got a ton of really high level generators, and then you have a run electric power like an EV, like an extreme voltage run, like 1,000,000 power capacity, like 1,000,000 power per second or whatever the EV. I don't even know what the values are, but let's say you have a crazy network in between. Well, you have on the generator side, you have them going into different transformers, right? So you have transformers, because transformers can go either way. You have all of these generators pushing into transformers. So on that side of the network, you have a bunch of generators, no consumers, and a bunch of storage. So in that case, looking in these loops, you have no consumer nodes, and you have a bunch of producer nodes, and you have a storage node. So you have like 3 gas generators on one side, but no draw. And then you have a transformer that takes, say, the MV power of all of those gas generators. You have 3 of them. Well, the transformer to go from MV up to, let's say, HV, right? That is going to have a huge internal buffer, right? The buffer inside the transformer will scale depending on what networks it's bridging, right? So an HV transformer, MV to HV, we could have 10,000 power in, buffer inside of that. And so in one tick, those generators will be able to push power into the transformer. Now, the network I'm talking about is on the other side of that transformer. you have HV transformer. And then you have a long wire system, and then you have another transformer, or several. They have a bunch of transformers, some of them going down to MV on the other side. Well, that network is just transformer. That's all it is. There's not even a producer or a consumer. In that case, we're going to have amount in storage, aka transformer on the generator side. We're going to have that amount in storage, and we're going to have the amount of available storage, right? So these two values are going to be key on the others on that network, because these are the only ones that are going to be relevant, right? They're the only ones that are going to be relevant. That is going to be an interesting case. I might even have to do an if statement. If there's no producer nodes, if there's no consumer nodes, then they're all storage nodes. Basically all transformers. That might have to be a special use case. That is, I don't know what the logic is going to be there. Because the available in storage, how would you do that? Available in storage. I'm not 100% sure how you do that. Because on one side, you have all of the transformers combined are going to have, let's say you have 6 transformers. Well, do you distribute power evenly between them? You say, the pool of energy that I have is this, which includes the transformer that's actually getting power, as well as all the transformers that are giving power to other networks. So let's say their combined total is 9,000 power that they have inside of them already. They're not either full or empty. They're just ticking along. So do you rebalance the power somehow? And how do you do that? We have the total that's available. Let's say that's 10,000, and the total storage available. Let's say that's also like 5,000. How would you then distribute all the power? I don't know how you do that. Because if you try to distribute evenly, that negates the priority system. So if you set a priority on those transformers, if you load up the GUI or whatever, and you set a priority, that transformer is going to fill first. Which, may be okay, but yeah, there's going to be transformers in that mix that are going to be filled first. The problem is if the transformer that's giving power, or it's supposed to be giving power, is higher priority. Because that's a problem. That one can't be a high priority. Because if that gets the power first, that means the transformer will be full at all times. And the network won't have any power to give, because the generators are trying to push power into a full transformer at all times, and those generators will eventually shut down because that transformer is a high priority. It's getting power, but it's full because on the other side it's a high priority, and it's getting power first. So 2 possible solutions for that I can think of, and if anybody later on down the road can think of another solution, I'm all ears. Two possibilities. One, YOLO and not care. If somebody sets that transformer to a higher priority, then it's up to them to fix it. And saying, oh, my network isn't distributing power, blah blah blah. It's like, well, check your priority. If your transformer feeding power into the network is a higher priority than all the other transformers on that network, that's the bug. Like that's how it works. It gets power first. So that's one option. Just say that's how the system works. Lower the priority and it will fix itself. I'm keen on that one. People will just have to get used to it, you know. People might complain at first and say, well, why is this blah, blah, blah. It's like, yeah, well, that's how it works. If you want a priority system, that's how it works. So, you know, YOLO is the first option. The second option is a little, I don't know. The second option is only allowing transformers one direction. Power in one direction. Which means, let's say that HV transformer. You have two flavors of transformer. You have high to low and low to high. Those are the two flavors. So the variance, you know, if we look at JSON code, variance, that's a really easy thing to do. You just have a variant. So they'll imagine, just ignore what these are actually saying. Let's say you have one, let's say the first type of variant is the first variant is power tier LV, MV, HV, EV. That's instead of like on, off, sleeping, it's LV, MV. That's your power tier. Now I'm just thinking that imagine this is a transformer block. So the first one would be power tier, and then one after that will be giving or receiving. Giving or receiving. So you'll have LV-giving, LV-receiving, MV-giving, MV-receiving. That way, it doubles the number of blocks that you include, which I'm less keen on, because this is already going to have a whole lot of stuff associated with it. So if you double the number of transformers, that can be a problem. But that also means that people are going to have to figure out which version they need, right? I have a bunch of generators. Which do I need, a giving or a receiving transformer? I don't even know the answer to that. My brain just sort of blue screened on that. If you have a bunch of producers that are all winding into a transformer, that would have to be a giving transformer. I'm giving power to the network. And then on the other side of that, the giving version would then go to all receiving transformers. But on the other side of that, oh man, yeah, I don't think that would work. I don't think that would work at all. So we might have to just default to the YOLO version. Because if you have a bunch of producers that are going into, say, the giving transformer, and then the network on the other side of that is a bunch of transformers, so you have one giving transformer, then you've got a whole bunch of other transformers. there's definitely a scenario. There's definitely a use case scenario that breaks that mold. I just know it. I just get the feeling that is because if you have a network on the receiving end, let's say you have a bunch of receiving transformers, you have a bunch of machines on there. Well, that's fine. But then what happens when you put a bunch of producers on that network? Then those producers cannot push into that transformer at all, which can be okay. But in that case, like, yeah. So in those cases, I think the easiest solution, honestly, the easiest solution is to lower the priority of the transformers that are supplying power to the network. Right? Because on the producer side, it doesn't matter. You've got 3 generators all on this network, and then 1 transformer. Maybe a battery in between, who knows? But you've got 3 generators and then 1 transformer. Well, it doesn't matter what the priority of that transformer. It just doesn't matter. Or you could have multiple transformers on that network. You could have a bunch of machines and have 1 transformer to an LV power, and you have a road now, you've got another transformer to LV power. You don't have a network in between. It's just that you have the generators on the same network as all of the transformers. And in that case, yeah, you need the transformers to be lower priority. You don't have to have them in that case. It's strictly the network of only transformers that you would need the supplying transformers to have a lower priority. And that you could, people when they play could just get used to that. Because all of the machines are going to have a default priority of like 5. That's kind of what I did in here. Priority 5. So when you first build it, everything's going to have priority 5, and it's up to the user to go in and customize that. I haven't done any of that code yet, but that's kind of how that's supposed to be done. Well, that was cold. Oh, I'm out of coffee already. Boy, this just does not last. Wednesday. So total power offered is including storage. So now, we know how much power we have total on the network. This value needs to then run through all of the consumer nodes. Again, I want to reiterate this for anybody who's come in late. I'm trying to minimize the number of time I iterate through these lists, right? Minimize these lists. Because, yeah, when you have really big networks, that's going to be a problem. You want to minimize the number of times you iterate. So we have total power offered. So we want to do for each electrical block entity in consumer nodes. I don't know what that IntelliSense isn't perfect. So now we are actually going to deliver power to the system, right? So total power offered is how much the power that we have available given our generators, if there are any on the network, and storage, which includes transformers. And I have been resisting this whole time to make a Transformers joke. So I hope y'all are proud of me. Okay. I'm out of coffee. Officially out of coffee. Coffee, I need more of you. I'm a little wired right now. I drink coffee too fast. Oof. I drink. Oof, that was a lot of coffee. Okay. So, we have all of the consumer nodes. Okay, so again, this might not even be here. So we have total power offered equals entity dot it's what is it? Which it's give power takes power offered and removes. There it is. Receive power. Okay. Total power offered. And then I don't even need false. Right? I don't need false. This is an optional. It's an optional call, but I'm going to keep it on there just for funsies. So this call is the thing that actually fills the machine with power. It takes the total power offered, takes what it wants to fill up its buffer, and then returns what it doesn't use, right? And then the next one comes in, and it uses, and it gives, and it just goes through there, right? Now we have to ensure let's try to prevent any bugs, because if total power offered is less than or equal to 0, that means we have depleted the amount of power on offer. So if total power offered is greater than 0, okay, we don't want it to ever drop below 0, because that would be bad. So when we get on the other side of this, total power offered will have any excess power. Total power offered will have any excess power we didn't use. Okay? So all that this does is this gives power to the machines here, consumer nodes. It actually iterates through. It should, quote unquote, it should start at priority 1, or it's going to be ordered by priority. I really, really hope that list is. If anybody knows whether or not this sort, right? I'm sorting. When I add it to the list, I immediately sort based on priority. And the question is, when I iterate through with a for each, does it start at the first one and work its way down every time? Because the enumerators, I don't know. I don't know if they do. That's something to obviously. Yeah, that's something to. What is this? Unnecessary assignment of value total power. Oh, geez. It's totally necessary. I need to control what this is, because this could be 0. This could be 0. This would add and then equal 0. Like I need to make sure that I'm doing this. Okay, so total power offered will have any excess power we didn't use, and it could be 0. Remember that. Could be 0. So now power in generator, total in storage. Total power offered. Okay, let's think about this logic. I'm trying to make this as simple as I possibly. So now I need to iterate through any generator, any of the producer nodes, and remove power from them. So we already have the power that we wanted. You notice I didn't do any if statement, right? I didn't do an if total power wanted is greater than total power off. Because it doesn't matter. In my mind, it doesn't matter if the amount of power wanted is greater than the amount of power offered. The procedure is the same, regardless of where the power is and where it's being used. I need to remove power. Now, if I do for each I electrical block entity in producer nodes, oh, come on. Okay. Now I need to remove power. And I need to use the restroom. All right. So anybody solve the conundrum yet? All right. So we need total power offered will have any excess power we didn't use. So the difference between total power offered and this like the difference between what this variable is now compared to what it is up here is how much power we actually used. Right? So which may not be how much we wanted. Wanted could exceed the amount that we used. Remember, these numbers can easily not match up together. So we may want 1,000 power, but we may only had available 500. Right? So total power offered might have been 500 power. The amount that we wanted might have been 1,000. So as it iterated through the consumers, it only had 500 power to use. So by the time we get down here, this is 0. Right? This is 0. total power offered is less or is greater than 0, and if we do an else, we break. Because if total power offered is less than or equal to 0, which most likely it'll equal 0, because this received power, it should only take as much as is offered, right? So if offered is 50 and it needs 100, it'll take the 50, set it to 0, and return 0. It should not take more. It's up to the author, the mod author, to make sure that received power, does the math right. But it should, and in the worst case, returns 0. So the next time it iterates through, it won't be greater than 0. It will equal 0. In that case, break, because there's no point in processing more nodes. There's 50 nodes, and we emptied out in the first 2 that are high priority. Then there's no more power left and bomb out. There's no reason to iterate through even more. So break out. Don't even process anymore if total power offered equals 0. So coming in here, total power offered will have the excess power we didn't use. It could equal 0. Right? So total power offered total power used equals total power in gen plus total in storage minus total power offered. Okay. So total power used, again, let's run through the logic of this. Total power used is this. I can't obviously use this, but is this, because we didn't edit this value or this value. These are still locked in. So this and this is total power offered. So that is essentially total power offered minus this, which is how much excess we didn't use, which could be 0. So if we used all of this power, then total power offered, which is this minus 0, equals all of the power. We literally used all of it in this case. But if this is greater than 0, that means this has the excess power, right? So total power offered, let's say this is 1,000, and then this is 50. This is the remainder of what we didn't use. So we had 1,000, and then we just subtract 50, because that's what's left over. So that's 950 power that we used. The total power that we used was 950 power. So now when we go through the producers, we need to remove the total power used, right? So total power used equals entity dot extract power. Total power used false. God, I love it. Look at that. IntelliSense just knows what the hell is going on. It's glorious. So this reduces power wanted by power held in this entity. So it's going to take the total power that we use. Now remember, this value cannot exceed the amount of power on offer, right? It cannot exceed those values. So we, at best, will remove all of the power from the from storage or from the producer, right? So at best, it will drain the power out of the system. Now, I don't have built in here. I don't have built-in limits of transfer. Let me say that again. I don't have limits of transfer for the network. So MV, LV, HV. The only limit that exists is in extract power, receive power, right? Those can be limited by the mod author. You can specify in that routine in your block entity if it has a limit of how much power can be accepted at a given time. All of the network cares about is shuffling the numbers around. It does not care what those numbers are. It's just shuffling power over here to power over there. Power over here to power over there. I'm not incorporating limits on how much power can go over there. It's going to be sort of an arbitrary limit based on the buffers in like transform. So like an MV LV transform will have like a 1024 buffer. Whereas an LV network, right, at any given second, the transformer is the buffer inside of a transformer will be 1 or 2 seconds worth of power. So if the generators die and there's no more power coming in, you have 1 or 2 seconds before those machines shut down because it's just out of power. That is an inherent limit on transfer speed. Now, it might take a little time for the transformers to completely, and there's a certain amount of unrealisticness of that, but I don't care. Right? You'll have transformers are essentially batteries with limited buffer. Now, you could on a network, you could place a giant battery that then will drain as the seconds tick by. And then eventually it would drain out, depending on how much power all of the machines are. So you could, I'm not going to limit the number of machines you can put, say, on an LV network. If, let's say, an LV machine, again, I'm throwing out numbers. Let's say on an LV network, the max you're going to be able to, like, if the transformer is 1024 and it's 2 seconds, which means an LV network should easily support 512 power per second. Easily. But let's say you're early game and not all of your machines are running 100% of the time, right? You have a bunch of machines, but a bunch of them are not operating all at once. So you have, it's essentially like turning on, like taking a circuit in your house and plugging in 1,000 lamps with 100-watt light bulbs. When they're all off, there's no problem. Turning them all on would be a huge problem. There's not enough power to run all of that. Same with my network. Same with these networks. Is you can have a ton of machines on a network, but the system itself will be bogged down if a bunch of those machines turn on. But if you're manually crafting a bunch of stuff, let's say you have a metal stamper machine, and you go and you punch a bunch of stamps, and that stamper machine is using 512. Let's say it's using 256, 128. Let's say it's 64 power. You go and you use the stamper at 64 power. Then you go over to another machine. The stamper's off. You go over to another machine that's 128 power, and you're using that, right? You're not exceeding the value of the power. So you could have 25 machines on that network, but they all could not be running all at once. If they all came on at once, you would have machines shutting down, just like in Minecraft. Minecraft is the same way. Minecraft, usually the power is first come, first serve, right? The power is going down, and it's just filling the machines as it goes down. There's no, like, priority system. It's an arbitrary, like, which machine is pulling power, that kind of stuff. Very bizarre way of doing it, but so in this case, the total power used can never exceed how much we have on offer. So total power used, we're extracting from producer nodes. Now again, this could be, there could be no producer node, right? This could be 0. And I think what I want to do, if producer nodes.count is greater than 0, like that. In this case, I think I want to do that, right? Because it's yeah, I don't know if this is the thing. I've already got the variable. If there's no producers, the variable isn't going to change. The total power used will not change. So for each electrical block entity in storage nodes. Okay. Now we have a conundrum. And yeah, it's weird, early times working on this. We had a decent turnout, but not a whole lot of people are interested in how the sausage is made, I guess. Okay. So here's the conundrum. Storage nodes can both receive and give power. So we need to remove power from these. But how do we give power that's excess? How do we give power? Let's first do total power used equals entity dot extract power total power used. Okay. If total power used is greater than 0. Okay. So let me go through the logic here. Again, a lot of this is just me talking out loud, kind of, figure out my brain. So if we have producer nodes on this, this will run and remove power from here. If we have some left over, right? If there's some left over, which means we used more than producers were able to supply. In this case, imagine there's 3 LV, there's 3 LV machines on a network, and then somebody adds an LV generator, like just a simple like Stirling engine. And so in that case, there is a producer. There's consumers, there's 3 consumers and 1 producer. There might not even be a storage node, but there is 1 producer. We need to make sure to extract power from that. And once we get through there, maybe it just drained all of the power. Reduces power wanted by power. So in that case, total power used could equal total power wanted. Or it could be less than total power wanted. So total power used in that case would have a remainder. Because total power wanted could exceed the generator, which means I need to extract power out of a transformer if there is one. So total power used equals NAD extract power, total power used. Okay. So this removes it from any batteries. And I would say batteries you want as a higher priority. And also the transformer. Total power used equals total in storage minus total power. Now my brain is kind of scrambled. Total power used greater than 0. Let's see. We have power that we used but wasn't supplied by generators. We have power that we used but wasn't supplied by generators, which is this. This is why I have so many comments in my code. Like, if you look at some of my code, there's a lot of comments because, yeah, this is a lot to keep track of. We have power that we used but wasn't supplied by generators, which this is the routine for that, right? So, when we get to the end of this, total power used should equal 0. Because remember, we cannot exceed the total in storage, right? Total power offered is the total amount that we had available 100%, including storage, including generators, including transformers. It is the absolute most amount of power that we had available. So that means total power used should absolutely 100%. Total power used should 100% should 100% equal 0 at this point. Okay. Now the issue is, so at this point, the power was distributed. The power was given to generators, or not, given to machines. It was taken from generators and taken from storage. Now, anybody out there listening, what step, what did we miss? We gave power to machines, we took power from generators, and we took power from batteries. There's one thing that we missed. And nobody's going to chime in because nobody's listening.
The transformers?
There's
Did you
one.
address those?
The transformers are included in storage.
Okay.
So the storage nodes, transformers are a part of that.
Yeah, sorry, I'm not paying full attention.
Yeah.
I can't really.
I understand. Neither.
Hopefully somebody out there chimes in.
So the step that we're missing, I mean, there's only like 1-2 people listening right now on the stream, but there's one thing that we missed, and that is giving excess power to storage, to batteries, or to transformers. Okay, so we've basically we've distributed power to the machines. We've taken it from any generators on the network, and we've taken power from batteries, but we haven't given power to batteries. So what's the formula? What's the formula at this point to figure out how much power we have available to give batteries? I think this statement is wrong. I think it's wrong. Because if total power used because this minus total power offered. Total power offered will have any excess power we didn't use. Right? So this value, total power offered, down here will have power that we didn't use. Total power offered. So what we can do, what should we do? Let me think about this for a second. We already know total power offered because we didn't touch total power offered down here. So that variable, right, that we used up here is still has in it a value. Total power offered still has amount of power we didn't use. So if total power offered is greater than 0, if there is power we didn't use, which means let's see. There's some edge case here that I could be a little bit more efficient, I think, with this. Because if we have generators on the network and the generators meet all of the demand of the machines, then we don't need to touch the storages. So that's an edge case, that you have enough generators on a network to meet the demand of all of the machines. Storages are not even a part of that equation. You might even have storages, but if you did, it wouldn't even include those. But I want to ensure total power offered still has the amount of power we didn't use. If total power offered is greater than 0 and storage nodes dot count is greater than 0, so here we have excess power and some sort of storage to put it in. Okay, so the storage, again, the storage will be also including transformers, and it might even include switches. So toggles. Not 100% sure how I'm going to handle toggles yet. But a toggle, what I'm going to try to prevent, because a toggle essentially bridges two networks. So you have network A on one side and network B on the other side. You throw the switch, those two networks are now combined, right? Power can now move, but you can break the switch, and now those two networks are severed, right? So it's easy to think about logically. You bridge the two networks, you sever the two networks. Now the problem is, on the network side of things, when you connect two networks, it has to iterate through all of the nodes of that network, updating its network ID, updating all of that stuff, and bridging the two networks. It's basically taking two separate networks, which we have all nodes here, we have all of these nodes. It's taking two of these and merging them together, right? That is going to be a memory-intensive process, because it's essentially taking one network ID and it's merging all of the next network. And then when you throw the switch back to turn them off, now it's severing that network. Now it has to generate a new network and then add all of the nodes back to that network. I don't think that's a good way of doing it, because that is a huge amount of shuffling of objects. So toggles will act like a transformer that you can turn off. That's my attitude towards toggles. I haven't gotten that far yet. Like, I want to get at least some form of this working before I really tackle that part of it. So toggles may just be included in a storage. They may have their own internal buffer, then they may act like a transformer, and then the block entity side of that, like a toggle, if the toggle is off, then it cannot receive power, right? Nor can it extract power. So that is a very special case. That is essentially a transformer that can get shut down, that can be turned off. And then the network won't be able to access power from it, and then it'll just use up, the machines will just sort of use up their buffer, and that's it. Then when you flip the switch back on, right, the networks are still ticking. The second you turn that back on, the next tick comes by, which is a quarter of a second, and boom, they can access that data again. And that ensures that the networks, they never have to be rebuilt in a network. Now you could break the toggle, which would break the block and break off the two connections, which that's easy to do in code. And then you could wire them together, and boom, that would call the merging of networks. That would do it. But that's going to be a special case. The merging of networks and the severing of networks is going to be a nightmare of code. It's just a nightmare. It's going to be a nightmare to rebuild the networks. And I would not do that on a stream, because that's again me banging my head on my desk for an hour and a half. Okay, so back to this. That was a tangent I didn't mean to go on. Back to this. So total power offered still is the amount of power we didn't use. So again, total power offered right here is how much power we didn't use, which ensures the total power used, we're actually removing that. We're not removing more power than we use. That was important for these. That was important. We're not removing more power than we used. And again, if y'all are thinking, well, what about rounding errors? Your fractional seconds, your fractional amounts of power. Again, I say the rounding errors is just the loss to heat, the loss to resistance that you get in natural power. It's built right in. How about that? We have a little bit of rounding errors. Well, that's life. So total power offered still has the amount of power we didn't use. So if that is greater than 0, if we have excess power that we didn't use, which should we compare that to powers in generators? Because if what we didn't use is in a battery or a transformer, and let's say you had a generator and a machine and a battery on a network. Again, you go through scenarios in your head, right? A battery, a machine, and a generator. The generator is producing 64 power per second. The machine is using 64 power per second. And the battery is there for whatever. So any given tick, if the machine is going and the generator is going, the power is being used, right? The generator is producing 64, the machine is using 64. So there's a net 0 amount of power. So in that case, total power used, total power offered includes the battery. But we don't need the battery. So total power offered will equal what's in the battery, which is like, let's say it's 1024, right? So that's 1024. So total power offered, okay. So if we're generating enough power, then the battery or transformer in this case won't be pulled from. Maybe we need to push into a transformer. Okay, so that case, we still need to process the excess power. But if all of the excess power is already sitting in storage, then why would we then push it back into storage? I think that would duplicate. That might be a dupe bug. If we're then pushing the power back into storage that we didn't use, that could have been a very bad duplication bug. Because in a network like that, generator, machine, and battery. Let's say the battery has 256 power out of 1024. So you have a generator producing 64, a machine using 64. So there's a net 0 there. And then the battery has 256. So in that case, the remainder, total power used is 64. But we have a remainder of 256. Because that was total in storage. 64 plus 256. Well, we used the 64. So what we have left is 64 plus 256 minus 256. So that's 64. Then we go through producers. We extract that's whatever power that we use, 64, whatever fractional version of that is. And then total power used is 0 because we used it all. So this is skipped altogether. But this value is still 256. It's power that we didn't use that we had available. Now the problem is we cannot then push that into a battery because we didn't use it. So I think we have to look at, compare total power offered, which is the amount of power we didn't use. So if total power offered is greater than total in storage, we have excess power and some sort of storage to put it in. And then this excess power exceeds amount in storage. Okay. Total power offered. Excess power, still is the amount of power we didn't use, is greater than total in storage. Which means, if we look at this, right? Which means the generators produced more power than we're using. There's a net positive amount of power in the network, right? So in that case of 3 objects, you have a generator, machine, and a battery. So the generator is producing 64, the machine is using 64, and the battery has available capacity, but it has 256. So in this case, when that machine shuts down and is no longer using power, now the generator is producing 64, the machine is not using any, and the storage is 256. So in that case, this power in generator, right, will exceed, will start building up. Or not really building up because there's space in the storage. So total power offered now is starting to rise because the generator is producing power, but the machine is not using it. So if we go look at the consumer nodes, machine is not pulling power anymore. Its buffer is full. The call is made. It's not removing any power, right? The total power wanted right here is 0. So there are little efficiencies that we might be able to do. You know, there's little efficiencies that we could do to sort of like logically eliminate tasks. And hey, Alex, all this takes me back to physics. Ooh, physics. Yeah, that's a rough class. And Dat, hey, welcome. Yes, thank you very much, sir. It's encouraging. So total power wanted is 0. Oh, my nose. Oh, the cat. Anyway, total power wanted is 0. Total power in generator is greater than 0. Total power in storage is greater than 0. So, in this case, if total power wanted equals 0, right, we could have a special case that literally if total power wanted is 0, which means there's no consumers. That means literally there's either producers or there's storage. So those are edge cases that we could eventually like cover to make this more efficient. But in the end, when we get all the way down here, right, total power offered is the amount of power we didn't use. If total power offered is greater than total in storage, will that ever be the case? Total power offered is power in generator and power in storage. Yes, because if the machine shuts off, power in generator is greater than 0. Total in storage is greater than 0. So total power offered is going to be whatever is in storage plus the generator. If we don't use any of that power right here, that means total power offered is greater than the amount in storage. Right? In that case, total power offered, which is the remainder, it's what we didn't use. So I could declare another variable to make this a little bit more readable, but I use comments. Still has the amount of power we didn't use. So we have excess power and storage. Remember, storage is also transformers. So now we have excess power and storage to put it in, which means we need to check to see if the amount that we have left exceeds the amount in storage, because this is not always going to be the case. If we're producing exactly how much we're consuming, then the total power offered will basically equal what's in storage. And in that case, if it's in storage, we don't want to deal with it. If total power offered is less than what's in storage, that means, what does that mean? Total power offered is less than. Total power offered will have any excess power we didn't use. Can this be less than total in storage? Yes. Well, let's think of that. Let's think of an example where the amount of power left over is less than what we have in storage. In that case, we have machines that are consuming more power than the producer and some of the storage, which means it's depleting the storage. Yes. Total power offered. If it's greater than 0, let's think of the network of just storage, just transform. Total storage available. I haven't used this yet. I know there's a reason I did that. So, total storage available. Total storage available. Which could be 0 if everything is full. Transformers, batteries, everything is full. Total storage available could be 0. But if it's not 0, means that there's storage left. This is one of those edge cases that my brain just goes around and around and around and around. Excess power exceeds the amount in storage. In this case, it means our generators and total storage available is greater than 0. Excess power exceeds amount in storage. Here, excess power exceeds amount in storage, and we have storage capacity available. Okay. I always when I have an if statement, I always when I go into the if, I always declare what is true when we're in this block of code, right? We have excess power and some sort of storage to put it in, which means that, right? That's what this says. And this excess power exceeds the amount in storage, and which is here, we have storage capacity available. So it's just in order to help my brain and maybe the other people coming after the fact understand what is being done in a statement like that. I usually have a comment that says, if we're in this block of code, this is true, right? And that helps me sort of cascade my logic. So in this case, excess power exceeds amount in storage, and we have storage capacity available. Then we want U-long total excess power equals total power offered minus total in storage. Total excess power. Make sure I didn't right. Total excess power equals total power offered, which again still has the amount of power we didn't use, but I need to remove how much is already in storage because I don't want to double up. This prevents it from doubling up. Yes, this prevents it from doubling up. Now, total excess power. Now, unfortunately, I need to do a for each I electrical block entity in the storage nodes, and then total excess power equals entity dot power wanted. Receive power. Total excess power false. So while up here for storage, we removed power, right? If total power used is greater than 0. We have power that we used but wasn't supplied by generators. So in this case, this will not always be run, but this will be run most time, right? So if we don't have any generators on the network, then all of the power that we're going to be using is going to come from either transformers or batteries. And so we need to extract what power that we used. Now, we may, if this is the case, this shouldn't run, right? Because total power offered still has an amount of power we didn't use. We should try to short circuit this. Total power used is greater than 0. Total power offered. Well, let's finish my thoughts here. Total excess power equals total power offered minus total in storage. Total excess power, receive power. So any storages, and again, transformers are part of that. Now, what happens if the generator has more power now we need to start thinking about like how to make this more efficient. So this total storage available could be considered part of total power wanted. Right? Because the batteries want power. Because in my mind, I'm thinking, this is fine and dandy, but what happens if the generator, let's say the battery has 5 power remaining. Or, yeah, the battery has 5 power left in its buffer, but the generator has 50 power in its buffer. This is a mind melt here. This is just melting my brain. I'm trying to do this efficiently here. Let's see. Total power wanted, total power in generator, total in storage, and total storage available. Okay. Total power wanted. Interesting that I don't use this. I don't use the total power wanted at all. Interesting. Interesting. I didn't even catch that. Total power wanted. I don't do any comparisons. I don't use it at all in this thing. Why even bother going through this loop if I don't use it? That's kind of a waste, don't you think? Total power offered, total power wanted. Total power. Okay. Oh my brain. Oh my brain.
tempted to look at some other like Minecraft mod to see how they solve this, but it's very, very hard to read a lot of those mods in their code and try to translate it. And then it's even harder to try to track down where those values are, like where the simulation is even being run. What the hell? Yeah. Weird. So obviously I'm using this mod as a very like loose inspiration for vintage engineering, immersive engineering. Everybody should be quite familiar with this mod. So let me give you an idea of why it's so damn hard to find anything in here. Not 100% sure where. Yeah, so you've got like wires. Everything is in Java, so it's again not directly. I mean, there's a crazy amount of code. But look at that. They actually named Catenary. Look at that. I had no idea. I have not looked at this in a very, very long time. But yeah, Catenary. Look at that. That's again, that's completely random. Where would the main energy wrapping energy storage? API.energy, which is basically what we're in right now. So you can look at like package this is like the namespace. So there are certain ways to do it, but I don't know what a record is. I don't know what a lot of this stuff is. Energy storage. Not really worried about energy storage. I just want to try to find like what, if anything, they have. Maybe it's not in API. Maybe it is in like main. It's not. It can't be in client. It's definitely not a client thing. Java. It's not in a resource. Resources is usually all the like JSON, the data, stuff like that. So loot modifiers, yeah, loot tables and stuff. Yeah, I don't think it would be under data. Client crafting energy. I don't think it would be under this. This is why it's like you cannot. It's so hard to find stuff in these, and sometimes they don't even include. Like I see a lot of client stuff. I'm not seeing a whole lot of server-based stuff. Yeah, see client. Where's the server? Entities, fluids, network. Oh yeah, those are a bunch of packets. Wires. Wire collisions. This is what zaps you, I'm thinking, when you run into the wires. I don't know offhand how to find data. It's not under data. Nothing's ever under data. API, energy, averaging energy storage. Update average. Average insertion, yeah. There's a receive energy. There's an extract energy. Again, these are coming from Forge. Right? Super. There's the super here. There should be package API energy. Anyway, I'm not sure why mutable energy storage, high mutable energy storage, high energy storage. There's what I'm talking about. High energy storage. So that's the interface. So receive energy, received equals super to receive energy. Return received. But I want to know what is simulating this. I don't know what calls this. Where's the network that actually is simulating the receive and extract? Where is these actually being called? I don't know. Show more. Mapping energy storage. Thermoelectric generator blocking. Dynamo blocking. Energy helper. So if I look at rotation acceptor, receive energy. Yeah, this is machines. I'm not even sure how this all works. Like where the electrical networks are coming from. Well, I mean, there's the wire. There's the whole wire setup in here. Main Java, yeah. Common blocks. Network. This is just all messages, which is essentially packets. I might have to include a bunch of that in mine. I'm not 100% sure yet. World wires. Yeah, the wiring system itself. Oh man, look at this, right? This is why there's just no way to directly port these. These are just an immense amount of calls to outside things. So looks like in Java, and I'm not a Java program by any stretch. Looks like in Java you have to import each object that you want to call, right? So you can't just include a namespace and include all of the things inside that. You have to include very specific objects in order to call them in, right? You have to include the wire type in order to call the wire type. Yeah, I've seen some of the files in here that this import section is like the whole first page. It's just unbelievable, 60 different imports. It's really, really hard to really see what's going on. Everything has been abstracted away really, really like hard. It makes it just hard to read. Yeah, energy wire. Get transfer rate, config. Yeah, I wish it was this simple to do a lot of this. Shocking wire, internal connection. Not sure where all this is coming from. So, again, I don't know what is actually simulating the network, what is calling the receive, and like what is building and tracking the network, or is it just super like, yeah, there all these imports. Oh my god. I don't know how it's built. I don't know how the actual system is built in here. So yeah, if anybody has any insight into how that's done, I'm all ears. But getting back to this, I'm trying to avoid as much like shenanigans in this function as I can. Like ifs, else ifs, all trying to avoid as much of that as possible. But it may not be possible to avoid it all. I'm not actually using total power wanted. That's a problem. Because I know it's important. Or is it? Do I even need to do this? Do I even care how much power is needed? All I care about is delivering power and storing excess power, if any. Can we simplify this even more by getting rid of this and this? Right? Because that would be great if we could skip this, even if we have consumers. Sounds like you're trying to cycle it. Yeah, I'm trying to figure out how to not remove all of the power. I'm trying to reduce the number of times I iterate through these lists, right? Because every time you iterate through one of these lists, it adds like lag to the whole system. Even in small networks, it still has to iterate through these. So if I can eliminate as much as possible while still maintaining efficiency. So in the case of how do we want to do? Let's okay. Let's do test scenarios. Okay. We have no generators, consumers, no generators, consumers, no generators, plus consumers. So we have, let's just do, okay. We have 0 generators, we have, I don't know, 0 generators, 1 storage. Transformer. Okay. So, and then you can just like, so we have 1 generator, 0 consumers, 2 storage, right? Just like, I'm just trying to think through scenarios in my head. 0, here's another one. 0 generators, 0 consumers, 4 storage. Transformer. Right? So, and then just logically, like, what does this mean to the algorithm, and how can we drill the algorithm down to apply to each one of these? You know, you can just keep adding scenarios if you want. So one scenario we don't have yet is let's do 2 generators, 2 consumers, and 2 storage. Okay. So 0, 3, 1, 1, 0, 2, 0, 0, 4, 2, 2, 2. Like, just how many different iterations? Even if we set this to 1, right? The number of combinations between the 3 of these is, you know, I think 9 combinations. 3 times 3? 9 combinations. So we could have 9 scenarios. So in this case, power in storage greater than 0. Power needed greater than 0. Power produced equals 0. Okay. Power in storage is greater than 0, which is the transformer. Power needed is greater than 0, which is the consumer. But power produced is equal to 0. Right? So power needed is greater, power in storage is greater, but power produced is 0. So then summarize this. Power produced is greater than 0. Power needed equals 0. Power in storage is greater than 0. But this transformer right here is power in storage. Let's put these in the same order. That would probably help. I basically reversed them, which is kind of funny. So the storage, power produced, 2 storage, 1 battery. So power produced is 0. Power in storage is greater than 0. Power storage capacity is greater than 0. And in this case here, power storage capacity is also greater than 0 because the transformer, remember, is a battery. Okay. So on this one, power in storage is greater than 0. Power needed equals 0. Power produced equals 0. Power storage capacity is greater than 0. Okay. So you can see all of the different little combinations because we have, you know, almost every one of these, you know, has power storage capacity, but we could come up with 0 storage. So now power and storage equals 0. Power needed is greater than 0. Power produced is greater than 0. Power storage capacity equals 0. Vintage engineering. What? Save as type go? What the hell type of file is that? .go? What is that? Can I just get a text file? Like, can that be an option? What? TypeScript? Where's .text? Something as simple as .text. Like, really? Let's just do power sim .text. You want to install the recommended Go extension? No, I don't even know what that is. Why is this? No, I don't want it. I don't even know what that is. Anyway, 2 generators, 2 consumers, 0 storage. So that means the power and storage is 0. The power storage capacity is 0, but we have power needed and power produced. So in my brain, I'm trying to figure out, is there a way to process this algorithm that basically allows for all of these different things efficiently? And, you know, the moving of material. Because we didn't ever use the total power wanted, we might be able to get rid of that altogether. Because we don't care. We don't really care how much power we want. All we care about is distributing the power that we have. So if we just straight up do that. Okay. So comment this out. We don't even need to use this, right? We don't even need to use it. So first thing we do is grab all of the producers, if any. So we could do if producer dot count is greater than 0. Okay. So if producer nodes dot count is greater than 0, let's go through and grab whatever is in here. Okay. Total power and generator. Now in this scenario, 0 generators, right? Power produced is equal to 0 because there were no generators. So power and generator is equal to 0. Okay, so now we need, how much power do we have in storage? If storage nodes is greater than 0, like that, storage nodes dot count greater than 0. Okay, this is just, you know, just in case. Okay, so producer nodes dot count, storage nodes dot count. Now, one of the things I could do is I have built in a feature in the network itself for sleeping. Okay, is sleeping. If the network is sleeping, that means it ticks at a slower rate. I have that built into all the machines as well. I think if I did I add that to the block entity? Yeah. So the block entities can also sleep. I have that also built into my test machine and test generator. If they go so long without updating, without changing anything, so I think I have it set to like 4 seconds. So if they go 4 seconds without needing or producing power, or if their power is full and they don't need any more, if they're not crafting a recipe on the machine side, if they're not burning fuel on that side, if they're asleep, essentially they put themselves to sleep. Then they tick at a slower rate. Rather than tick like 4 times a second, they tick like every 2 seconds or every 4 seconds. And that reduces the weight on the tick rate, right? If you're just bouncing out, and as soon as you add fuel and the next update tick comes by, and it detects, ooh, I've got fuel, start burning, it wakes it up and starts burning it, right? So there's a tiny delay in interacting with a machine, like putting an ingredient in, and it waking itself back up. Now what I'll probably do is have some UI functionality that when you open the UI, it immediately wakes the machine up, right? So rather than wait for it, it actually opens it and it wakes it up right away. So the network itself, on the network side of things, can also go to sleep. So let's say you have a nice big network and you've got a big HV, like high voltage line, and that's going down into an MV line, and the MV line goes down and it's going into a bunch of LV lines. And if you've got one of those LV networks that's all of the machines are off, they're all full, the transformer is full, everything is full, and it's just sitting there, right? None of the machines are on. All of the machines are actually sleeping, because you can go through each machine and see if they're all sleeping, including the transformer. And if they're all sleeping, then you can mark the network itself as sleeping. So that's another thing I want to do in this update tick, is track what is sleeping and what isn't. But I'll worry about that later. Okay, so we have producer nodes, we have total power and generators. We have storage nodes. Now we know how much is in storage and how much storage is available. How much storage capacity is available, which means how empty are they. If this equals 0, storage available equals 0, then all the storages are full. Well, I don't think I care about that. So, if consumer nodes.count is greater than 0. Okay. Now, again, all the consumer nodes, if there are any, all the consumer nodes get power. The total power offered is still the same. Power is in the generators and the total in storage. So at the end, this is still available, total power offered will have any excess power we didn't use. It could equal 0, which means we used all of the power we had available. So I need to know eliminating this will help, especially on big networks that have a whole bunch of machines. So you have 20 machines, like 20 LV machines on a network. Well, avoiding doing this, that's 20 machines that I'm not iterating through. I'm just iterating through. If you have 20 machines on a network and a transformer, well, I don't care about this. All I care is how much power is in that transformer. There's no producers, so that will skip that. It'll go into here and say, well, how much is in storage? Well, the transformer has 1024. So this will be 1024. Let's say the transformer is full. Available is 0. So it has 1024 in it. All I need to do, total power offered, will be 0 plus 1024, which is 1024. Come in here and say, okay, well, let's iterate through all of the machines, all the consumers. We have 1024. Let's distribute that. 1024, blah, 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 blah. Going through, bomb out, once you get out of that, if you iterate through all of those machines, whatever you have left is what you didn't use. So now, power used, in that case, is how much power we used in the storage, right? It's how much power we used in the storage. So, what I could do, if I declare like 600 variables, I just want to make sure that we do it right and it's not gonna just waste memory. So I could grab the total power used, but I could also grab the total battery power used, right? Total in storage, total power in gen. So let's just for total storage used equals get rid of that because it's confusing me. IntelliSense. Total storage used is what? Total in storage what do we want to do here? I'm making these variables just to help my process here a little bit, just to help my way of thinking. Total storage used is what variables? And remember, I'm considering this as well, and I don't think there's a way of increasing the. Yeah, I don't. There's a way to do it in Notepad, but for some reason, I have not figured out a way to increase the text size in this document. Like control wheel doesn't work. There's no scroll bar here. Usually there's like a text size scroll bar. I've got one over here. Oh, maybe not. But I know control mouse wheel does what I want here. But for some reason it doesn't do it here. Anyway, if anybody knows how, let me know. So the scenarios I mean, if we only have storage, that's easy. But we have such an interesting combination of things here that we need to figure out how, given all of this up here, producer and storage, total power in gen, total in storage, total power offered, power in gen, which could be 0, plus total in storage. Then we get through here, total power offered. But power in gen might be greater than 0. So why am I having trouble thinking of this? My brain is starting to break down. Total power in gen plus total in storage minus total power offered. The total power offered has now, when we're at this point, total power offered is actually something different. Total power offered will have any excess power we did not use. So total power used will be let me think this through. Will be total power in gen why is that power in gen? Total power in gen, which can be 0. Total power used. Total power in generator. Storage used. We need to take whatever we used. Total power in gen plus total power in storage, or total in storage, which is our total power. We subtract what we have left. So that actually gives us the total power that we used. Now, it could be 0. Total power used itself could be 0. But we want to take the power that we used total power used, subtract total power in generator. So now we're taking this, which is the amount of power that we used. We're taking that, how much we used, subtracting how much we're in generators, which again could be 0. The important thing is in here, we do not divide by 0. So none of the values are being divided by anything. So total power in generator can be 0. But we take the amount of power that we used, total, we subtract the amount of power that's in the generators. Because we use that first. Right? Total power we used minus the total power in the generator. So in this case, I don't even need the parentheses on this. In this case, total power we used minus power in generator will return how much storage we actually used. Right? Anybody come up with a scenario that's not the case? Even if we have no generators, right? If we have no generators, then that will be 0. The total power used then is whatever is in storage. If power and generators, let's see, total power used. Power and generators. Now, the problem here, total power and generators. Can this ever be negative? Can the power we used ever be less than the total power in the generator? Yes. Yes, it can. Okay, that's a problem. That's a problem. That's a big problem. So there's something fundamentally wrong with this. There's something wrong with this. Total power used, because let's look at a scenario. Just add a scenario. 1 generator, 2 consumers, 2 storage, 1 transformer. Okay. So what I say when I'm talking about like coming up with different scenarios, you know, all of these include 0 in something, except for this one now. So now, power in storage is greater than 0. Power needed is greater than 0. Power produced is greater than 0. Power storage capacity is greater than 0. Right? So now all of these are in play in this scenario. 1 generator, and you can replace these numbers with any other number, right? As long as they're greater than 0 or equal to 0. You can't have negative consumers, by the way. So, you know, 0, 0, 1, 1, 1, 0, 1, 0, 0, 1, 1, 1, 0, 1, 1, 1. You know, and there are other combinations. Let's see, 1, 1, 0, 1, 0, 1, 0, 0, 1. I did that. 0, 1, 0. I don't have that, but that is just 2 consumers. If all you have on a network is 2 consumers, you're not going to get very far. You could have a network of 2 consumers, but there's going to be no power to deliver, so it's moot anyway. If you have a bunch of generators on the network with no storage and no consumers, you're, again, not going anywhere. There's nowhere to put the power. You know, I still have to test that, but anyway, total power, total storage used, total power used, minus total power in generator. So in that case, right, let's say you have a generator, 64 power, you have 2 consumers, it doesn't matter, and then 2 storages, which is a total of like 512 power. You have 64 power, and then you have 512 power, which gives you total power offered, 64 plus 512, 576. Then you come through here, and the consumer takes whatever. It could easily be less than what's in storage. So total storage used this needs to at some point equal 0. There is a scenario where total storage used needs to equal 0. All right, I need to use that. All right. Okay. So yeah, there needs to be this formula needs to include a scenario where this formula comes out to 0, where we do not use any storage. Okay. So total power used could equal total power in gen. Right? So total power used minus total power in gen, this would then equal 0. Which would be total storage used equals 0. But then we look at total power used. Let's say it used not only what it was in the generator. So it used all the power in a generator. Let's say a bunch of machines turn on. You have one generator, but a bunch of machines. And so all the machines all turn on at once. The generator only supplies 2 of them, or 1 of them. The other 2 are pulling from somewhere else, basically storage or a transformer. So the total power in generator plus total in storage minus total power operate, which is the remainder of what it didn't use. So in this case, total power used is greater than the power in the generator. Okay. So that in that case, total power used is greater than, which means there was some storage used. Now, can the other scenario be present? Total power used. In the case of a generator, let's say you have 3 generators, 2 machines, and you have a surplus of power, right? The generators are producing more than the 2 machines need. So in that case, the total power in generator is greater than the power used. Right? So that means this would be negative. If total storage used is less than 0. Total excess power. If total storage used is less than 0, which is a weird situation to be in. If it's less than 0, total excess power equals total storage used absolute value. I mean, might not be able to make this work because, yeah. Actually, it can't. It's unsigned. Okay, that's a problem. It can't ever be 0. This is a problem. It would be well, I'm glad I caught that. Decimal.max value. Whew. That's a big number, but constant representing the largest possible decimal value. The value of this constant is 100,000, million, billion, quadrillion, quintillion. Holy Moses, that's a big number. Yeah, because I'm using unsigned values here. Huh. If total power used is greater than total power in gen, or equal to. So total power used is greater than or equal to this value. Okay, total power used is greater than or equal to total power in generator. Okay, which means, again, I always, if I'm confusing myself, then I put some comments in here. We used more power than generators were able to provide. Storage was used. Else, total power used is greater than or equal to. So the only other scenario is when total power used is less than total power in gen. We have excess power produced and not used. Push into storage. Okay, So that means total excess power equals total power in generator minus total power used. Right? I'm switching this value here. Now it's subtracting this value. Because, again, because these are unsigned. The U is unsigned, which means it cannot be negative. So I want to ensure that we do not roll over, because if you have an unsigned number, whatever that number is, 50, if it's unsigned, and then you subtract 60 from 50, it could either A, go to 0 and just null it out, but depending on the language, it could roll over into a very large number. And that's what happens in a lot of games. When you see little exploits, when you see little glitches where you have, let's say, money, and you spend, let's say you have $1,000, and in a game you spend, if there's some glitch that allows you to, you have $1,000, and then you spend $2,000. Well, if you cannot go below $0, it can roll over, and suddenly you have $2 billion because it rolled over, right? There's a word for it. I can't even think of it right now. But so what I want to make sure is that total storage used, we have excess power produced and not used, which means total storage used will be still 0, right? Because total power used is less than power in generators, which is what this is. So it doesn't touch this. This stays 0, and then it goes to this, total excess power. So with this little block here, I have solved whether or not we have excess power to push into storage. We've already delivered power to the machines. That's done. That's already done. Okay. We've grabbed the power in the generator. We've grabbed all the power in the storage. And now we have excess power. So here, depending on what we have here, right? We used more power than generators were able to provide. Storage was used. Now we have this. Now we need total storage used, total power used. Now we need to iterate through, because these are two distinct scenarios. We either did not, or we either did use storage, or we didn't. Those are two distinct binary, like that's mutually exclusive. You cannot have both. You cannot have both be true. It's one or the other. So we used more power than generators were able to provide. So we need to remove total storage used. We still have this total power used, right? So in this situation, if producer nodes dot count is greater than 0, we need to do that. And then storage was used. I know storage was used if I'm in here. So we remove power from any generators. Now, there may not be any, but I know we actually used power from storage, which means For each I electrical block entity in storage nodes, okay, total power used equals entity dot extract power total power used false. Right? Now we are drawing the amount of power from the batteries. Now, is there ever a scenario where okay, let's not confuse ourselves here. We have excess power produced and not used. Push into storage. Do we want to use this? Total storage used. Total power used. We shouldn't ever exceed the amount of power offered to consume it. Because we have, let's see, we have, I feel the cat. The cat is up and around again. You want to come up here? Sometimes she just sits down there and stares at the tree. There she comes. Yeah. Show the butt up. We shouldn't ever be using more power than we have. Right? Because we have total power offered, which is the sum total of all the power. So power used should never exceed power offered. Period. You're not going to be up here for very long. Are you okay? Now, the closer we get to winter, the more time she's gonna spend in the lab. Oh, the purrs started. Yeah. Yeah. So total power used it's impossible to actually exceed the amount of power offered because I have that if statement right there. Total power offered is greater than 0. So as soon as that hits 0, it'll bomb out of that. So yeah, it may not fill all the machines. There's a bunch of machines that'll just fill them by priority. So yeah, that should be fine. So yeah, total power used should never exceed total power offered. Total power offered will have the excess power we didn't use. That's fine. So total power used down here is what we're actually pulling. We're not pulling offered. We're just pulling the used. Whatever we used, that's what we want to grab. So if total power used is greater than or equal to total power in generator, which means we used more power than generators were able to provide, storage was used. So total power used exceeds the amount of generators, which, let's face it, is going to be the case most of the time. So the storage, including the trans thing, transformer. Boy, my brain just couldn't think of the word. So in that case, yes, power was used. So by the time we get to the end of that, total power used should equal 0. If total power used does not equal 0, logger dot here. What? Oh yeah, I don't have access to the API. If total power used does not equal 0, which is a problem, throw new exception. I'm just going to put this in here. I probably won't leave them in here, but it's a good thing to put a breakpoint on when you're debugging, to have like catches like this. Put a breakpoint on that. That way it'll bomb in here if that case happens, and then you can sort of debug it from there. Did not consume all power used. Did not consume all power used. Got a good description of what this is. Total power used. Did not consume all power. Yeah, it should be zeroed out by the time we get out to here. We should have consumed all of the power because storage was used. We don't have access to power. We have no power left to push. So in this case, yes. The purrs and the chin scritches. Yes. So now I think this routine is essentially done here. So now we have excess power produced and not used. Push into storage. Total excess power equals total power in gen minus total power used. Simple, straightforward. It's the excess power. It's the amount that is in the generator minus the amount that we used. Now, here is, well, no, let's push into storage, and that includes transfer. Because transformers, you'll be able to push either way. So let's get this first. We have excess power produced and not used. Now, this value will come into play. Storage available. I'm ignoring all this down here. Total storage available. I need to know so there's two possible scenarios here. Either the excess power exceeds the storage capacity or it doesn't. If it's equal to, then that's the same as not exceeding. But it either exceeds it or it doesn't. So I think there's another binary in here. There's another if statement. If total storage available is greater than total excess power. Storage Available storage capacity exceeds leftover power. Leftover power exceeds storage capacity. Push all power into storage. Push or fill. Now, what do I want to do? Summarize that. Push all power into storage. Remember, I only want to remove from the generators the power that we use. I don't want to just empty the generators, fill up everything, and then void the rest. That's not good. Leftover power exceeds storage capacity. Remove only what is needed to fill storages. Okay. I hope everybody is following along. I'm hoping I'm making this at least understandable logically. So this might look like a lot of code, but remember that these situations, this block of code, if this block of code runs, this one doesn't, right? If this block of code doesn't run, then this one does. So it's, it is, even though there's, there might be a bunch of loops, only one of these will ever run, right? So if this one doesn't run, this one runs. And if this one runs, only this one will run. Or only this one will run. Oh, there she goes. Oh, the fur is real. So even though there's, some shenanigans going on in here, I'll probably be able to delete all of this, but I just want to logically think through this. Push all power into storage. Okay. But again, we're not processing our producer nodes, right? Available storage capacity exceeds leftover power. Right. We have excess power produced but not used. Push into storage. So we know that the producers, we need to drain a certain amount of power from these. How much power do we want? We want to push Okay, let me just think about this for a second. My cat distracted me. We have excess power produced and not used. Push into storage. In the case of that, we have all into storage or partial. So if it's all going into storage, then we want to grab all of it out of producer nodes. Okay. So, how do we do that? Total power used. That is what we need. So, we can just copy that. This, again, total power used is here less than total power in generator. We have excess power produced and not used. So what variable, total power used is greater than or equal to, so down here it is less than, total power used is less than total power in generator. We have excess power produced and not used. So we want to actually depreciate total power in generator. Right? Which will drain everything out of a generator. Right? If we're taking the amount of power in the generators and then we're looping through the generators and removing that much power, then in the end, total power in generator should be 0 coming out of that. Granted, there might be some rounding errors, but whatever. But we should zero out this. Now, I could take total power in generator, add 100, and just pass that in, and it will depreciate. It'll drain all the power, regardless of what rounding errors you get, and that will ensure all of them. I should actually do that. So total power in generator plus equals 100. This will ensure all power is removed from generators. Okay. So this is pushing all of the power, or this is essentially extracting all the power from the generators. Okay. Regardless, I don't care what those values are. I just know that our storage capacity exceeds it. We're going to push everything available, and we already have how much excess power we have, right? And so here we do for each high electrical block entity in storage nodes. This is going to be total excess power equals entity dot receive power, total excess power, false. Push excess power into storage nodes. Push excess power into storage nodes. Okay. So again, we have excess power produced. Available storage exceeds leftover power. So the generators, total excess power. Push all power into storage. So where did I do total power in gen? Okay, there it is. Available storage. Total storage available is greater than how about greater than or equal to? Greater than or equal to. Very rarely will they be precisely equal to, but we want to make sure that we cover that. Okay, so total storage exceeds or is equal to how much excess power we have. That's what I was missing. My brain was just sort of like, what? Did I do something wrong? So we know that we have enough storage available to take all of the excess power, right? We have enough, which means we're not using storage. We're actually able to push into storage. But again, leftover power exceeds storage capacity. So only remove what is needed to fill storages. So this is the last possible, I think, scenario. Okay. So we have excess power produced and not used, push into storage. So we're calculating how much excess power we have, which is in whatever's in generator minus whatever we used already. And yes. And then we look at total storage available. And we say, okay, well, now we have push power into storage. We have plenty, if let's say you just build it
generator starts up and the battery is empty, right?
And it's just going to start filling the battery. We have excess power and we have plenty of storage. Now, as that battery, what if that battery is full? Now, total storage available is not greater than or equal to total excess power. And now we're going to be down here. Leftover power exceeds storage capacity. Remove only what is needed to fill storages. So here, doesn't matter how much storage is available. How much storage is available? Or do we, because I could do another if else here, if total storage available equals 0, right? If there's no storage available, why even bother? So that could be an efficiency that I do. So if total storage available, now we want leftover power exceeds storage capacity. But I still need to remove we have leftover power, but I haven't removed the power yet. Which means I only need to remove, well, yeah. Leftover power exceeds storage capacity. Total storage available now means the total power used see, me not using total power used here is going to bother me. I need to only remove the power that was used plus whatever storage capacity is available. So U long total power consumed equals total power used plus total storage available. So total power consumed here, leftover power exceeds, is the total power that we use, which is way up here, is the actual power that consumer nodes received. So this could be total and storage minus power offered. You notice that I'm going through the consumer nodes just once, right? I'm pushing power into them because there will always be in any given network, 99% of the time, there will be more consumer nodes than there will be producer nodes. Right? The upper echelon tiers of power generators will be able to produce enough power for many, many dozens of machines. So you'll have one producer on one network, but you could have a bunch of networks that's just all consumer. So consumers, I wanted to make sure that we were not iterating through this list more than was absolutely necessary. I even took one of them out because it's like, yeah, I don't want to mess with that too much. So now, down here, wherever I am, right here, total power consumed is the power that we used, which is coming from way up here. And again, this could be 0. Remember that. This could be 0. 0 is less than, say, power and generator, which comes down to here. Total excess power. Total power used is 0. Total power in generator is XYZ. If that's the case, total excess power equals total power in gen, which means the total excess power equals power in generator, total storage available, Well, that's coming from all of the storages, including transformers. So logically, you can run down the list that we did here, right? And include scenarios and be like, all right, how does my logic work? How does it cascade down? And so if you have a network that's just producers and a transformer, right? That means total storage available is the transformer, which will always be less than the total excess power, which is the power in the generator. Because you have generators, they're just constantly generating power. Total storage available, we might have an empty, it's an empty transformer or whatever. So I'm just logically making sure that we follow it here. So coming down to here, leftover power exceeds storage capacity. I'm really glad I wrote these comments. This is very, very helpful. Leftover power exceeds storage capacity. Remove only what is needed to fill storages. This is only what is needed. The power used plus the storage available. And the storage available is just a little bits in either batteries or transformer. Is whatever storage is available in there. And now we have how much power is consumed. So now we can iterate through the producers, right? So if producer nodes dot count greater than 0, for each electrical block entity in producer nodes, I can do total power consumed equals entity dot extract power total power consumed false. Okay. So now I'm removing from the generators, right? I'm removing from the generators only the power that we need from the consumption, right? Whatever we used and the storage we have available. So once we have the producers, once we've lowered whatever little bit of power from the generators that we need, now we want to, for each electrical block entity in storage nodes, okay, in storage nodes, you could even do like dot where. You saw that dot where, right? You can even do like, you can limit the list with a link. You could do like dot where, and then you could specify only the storages that have access, like the amount of power. But that is a call that, I mean, I think it's faster just to iterate through all the list, because there could be 5 in there, right? It's not worth a call to a link library to try to sort, and I mean, it's just try to sort 5 things. Now, if you have 1,000 batteries on a network, that's on you. Build a bigger battery. Yeah. So it's up to the user to try to be efficient, but I can't cover everything. Okay, so total power consumed equals entity dot store dot receive power total power consumed false. Okay, so this might be a little confusing. Let's make sure I did this right. Okay, so what we're doing here, we have the total power that we need. This is the amount available in storage and the amount used by machine. So when we iterate through all the generators, we want to remove power from there while reducing the total power consumed. So we're reducing the power consumed. Now, coming through here, total power used. No, we don't want to use that here. Takes power offered and removes any power needed and returns the leftover power. That's not going to work. We want to reuse total storage available. Okay. So, at this point, total power consumed equals 0. And total storage available equals 0. At this point, total power should equal 0. And this should equal 0. Because we've consumed the amount that we needed and we've filled the storage available. Right? Now, of course, there could be some odd rounding error. Do we care? Now, I could add a call if we look at electrical block entity, right? I could add a call in here to just fill power. Right? Instead of doing like the same call over and over again, extract, receive, if I know, in this case right here, I know that we're filling the storages. We're just flatly filling. We don't care what the remainder of the power is. We already know going into this that we're going to fill them all up. We've already removed the power we're going to need from the generators. So we know we have enough power to fill the storages. Likewise, this call, right? This call, we know in this loop here, in this block, we know that we're going to remove all of the power from the block, from the entity. We know, regardless of what it is, we are going to zero out the amount of power. So all this is doing is extracting the amount of power we need and returning what power we weren't able to deliver. So it's literally zeroing out the power. It's lowering this value by how much power was available and returning it. So the next one gets it and it's like, oh, I'm going to zero out my power. So we could add two calls. We could add or I don't know, max power, current power. See, these are just getters. This is not we don't have a set. So this is only read only. Right? The current power, I can't set current power to equal something. That is up to the block entity to process, and that's what these are for. But I could do a void drain power and a void fill power. Okay. So let's say I have those. Where are my 5 references to this? Oh, yeah, duh, in the thing I'm doing. So you can see this is an interface. There's no code in the interface. It's just defining what the pattern needs to be. Any block that institutes or integrates this interface will be forced to implement all of this stuff in the interface. So drain power or fill power. What I could do, I could combine these to what could I do here? And now all my concurrent views dropped off. Well, that's just not. Instead of having two of these, what would I name? What would I name something that would just override the power? One procedure that would both be able to drain it and fill it, depending on like a Boolean value passed. Because that would be a quick call. That would be a really, really quick call. Just a really simple procedure that you just, on the block entity side, if it's called, and let's say the Boolean is do fill, well, if the Boolean is true, you just fill power. If it's false, you just empty power, right? I mean, this is really, 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 really simple. But one call that would be able to do both of those would be very, very handy. So how about we... What would you call it? I can't even think. Like, what the hell would you call it? Override power. Give power, extract power. Power. Yeah. What the hell? Like, what would you call it? To just like override it completely. You're not trying to simulate. I can't even think of a word that would go there. I could do like cheat power. Bool drain equals false. Right? So cheat power will completely fill power buffer or completely drain power buffer if drain equals true. A shortcut, a fast way for electrical network to process power for this entity. Drain power to 0 if true. Okay. So cheat power, right, is or could be, it's a void. All it does is either max power or drain power. Now, you could, because it's cheat power, you could add a mod that adds a key, like a command. Like I could even implement it in the mod itself, where you could just type a command, and that would set it. You know, it would just set cheat power, and it would just loop over any network and cheat. You know, and just fill the power or drain the power or whatever. Maybe, you know, I'll look at it later. But with this will ensure all power is removed from the generators. Rather than doing this, let's see. Remove all power from generators. So rather than doing this, we're going to do entity dot cheat power true. Okay. Extract power, which is draining the power, which sees true. So entity dot cheat power true is pulling all of the power out of those blocks. And I'm not returning anything. It helps the stack, right? When I make a call, if there's no return type, it helps keep stuff off the stack, which is very, very handy. Push excess power into nodes. I just want to make sure that we're not manipulating or not missing something that we should. We use more power than generators. Arrived storage was used, which means, yeah, I don't necessarily want. Okay, cheat power. Remove all power from generator. Does not track or return any value. Push excess power into storage nodes, which is fine. It may or may not fill the storage. Because remember, storage available is greater than or equal to. So the excess power could fill, not guaranteed. But down here, we are extracting total power consumed. But this call, entity.cheat power, fills power buffer in storage. Fills power buffer in storage. Because we don't need this value anymore. Total storage available, we don't need it. We already know power exceeds storage capacity. We already know that we're going to be filling all of the storage is up to the tippy top, and that's it. I think that is it. I don't think we need any of this code. Total power used, and we have the power used. Yeah, this was old. Okay. Let's go through this and look at the scenarios. Remember, we got scenarios in here. These are just all little tips. 0 generators, 3 consumers, 1 transformer. 0 generators, 3 consumers. So 0 generators, but 3 consumers. So that means we're going to go through here. There's going to be no producer nodes. No. Yeah, 0 generators. There's going to be none of these. We're going to go through here. There's going to be 1 storage node, which is the transformer. So we're going to have a total in the storage, which is the total in storage. And we're going to have maybe a little bit of buffer out. You know, maybe the transformer isn't full. Now, in this case, total in storage, total storage available. We have some power, but remember, we have 3 consumers. Right? So we go through here, there's 3 consumers. So now we take the total in storage, which is already added, which is the total power offered. So in this case, total power offered equals total in storage. We receive power. We're deprecating total power offered, which when we get back to the other side, right? When we get back to the other side, total power offered will be what power we did not use in the storages. So it could be 0, but it likely won't be, but it could be 0. So total power used is greater than total power in generator. Well, we didn't have any generators on this network. So this is true. Just right off the bat. We did not have any generators. There's no generators. So this is definitely true. Total power used is greater than total power in generator, which equals 0. This total power in generator is 0. So total power used, we used more power than generators were able to provide. Storage was used. Blanket term, storage was used. So now we have total storage used was total power used minus power in generator, which again is 0. So now total storage used equals total power used. So we go through producers, of which there are 0. So we don't go through those. There's 0 producers. We go through the storages and we say total power used. We extract that power from the storages, right? We should be 0 at the end. We should be 0 at the end because we took all of the power out of the storages. And we know that total power used is greater than or equal to power in generator. So, total power used is greater than total power used. What happens? Wait a second. I just thought of a possible bug. What happens if the total power in the generator, total power in storage is less than let's say you have 3 machines. Let's go through here. We have 3 consumers and 1 storage. Now, let's think of the case where combined the 3 machines need 1,000 power total. But the transformer only has 500. I come up with simple values because it's just easy. They're going to be tiny fractions of value, but in this case, just think of different values. Is my stream still going? It is. I just don't know why nobody wants to watch. So in the case where there's not enough power in the storage, where this iteration, total power offered, is 500. It iterates through the consumers. It drains it all. Power offered equals 0. It breaks out of the loop, comes down here and says total power used equals total in storage, which is 500, minus 0, which is 500. So total power used is 500. There's no producers. Again, no generators. No producers. So we come down here. Now, total power used is 500. So we extract the 500. We iterate through the storage, which is just 1. We literally extract all 500 out of there. Total power used will equal 0. Okay, so that checks out. That checks out. I was worried that it wouldn't. So what happens if the power used what happens if the generator or the machines need 200 power and there's 500 power in the storage, in the transformer. So now we need 200 power, but we have 500 power. So logically, let's go through. We don't have any producers. We have storages. Total in storage is going to be 500. Right? So total power offered is going to be 500. We're going to go through here, and we're going to have this. Remember, when it gets through here, we're going to be minus 200. So by the time we get down here, total power offered will be 300. The 200 will have been removed. So now this is 300. So now total in storage is 500. Now we subtract 300. So that gives us 200. 200 is still greater than power in generator because that's still 0. So we come through here. Total storage used will be 200. Minus power. Yeah, this will still be 200. So this, again, won't run. This won't run at all because there's no producers. We come down here and total power used, again, is 200. And we extract the 200 just with one bop. Just remember, there's one transformer. Extract 200, boom, power used equals 0. So both scenarios they actually work out. And when they equal, it also works out. That's why there's a greater than or equal to. So that scenario works out, regardless of what power combinations you have in there. So let's look at a very, very different scenario. Storages. If all you have on the network are transformers, which is more than possible. It's very, very possible. Right? If you have a bunch of generators pushing into a network, and then you have that network managed, so you're taking a bunch of like MV generators and you're pushing it into an HV network. You have a bunch of transformers. The generators are feeding all those transformers. Those transformers are then on the HV network, and those go down the line. Whatever the wires, I don't care about the wires, but if they just run down, now you have one or more transformers feeding power and one or more transformers removing power. Now, how does it work in that case? Let's check. We have no producers. Right? We have no producers, so that's 0. So power in gen is 0. Storage nodes. Now, we are not discerning ourselves with what transformers are, what direction the transformer is going. Let's see if that works. Let's see if we can generically use transformers the way that I want to. So we iterate through the 4? Yeah, 4 transformers. We combine how much they have in them. So let's say the two supply transformers. We have 2 supply and two transformers getting power from generators and 2 transformers delivering power to other networks, LV. So in that case, the total in storage will equal what the 2 generator supply transformers. Let's say it's 1,000 power. The other 2 transformers are 0 power. They're being depleted. So they're 0 power or any deficit thereof, which means their total in storage will be added to the list, but they'll be less than possibly than what we have available here. So the way I look at it, a transformer only network will auto balance itself. So the levels, percentage full of the transformer will auto balance, where the lower transformer, right? So if you have an MV to HV transformer, that's getting power from a bunch of generators. So that network is actually pushing power into the transformer and filling up the internal buffer. Then the other side of that network equation, with just the transformer, it's seeing that internal buffer and saying, "Ooh, I've got power in here. Let's add that to what I'm accepting." And it's other transformers in that network. Those values, those buffers will be up and down, but I'm looking at all of them I'm looking at all of the storages, and I'm saying, okay, here they are. Now we're assuming the priorities are all equal, because when you start messing with priorities, it can easily cause problems. So then it's first come, first serve, whether or not it's remove or add. So on the add side of the network, if you have 4 generators hooked up to a transformer, well, the transformer is the only storage block. It doesn't matter what its priority. But on the other side of the network, on the transformer only side of the network, that priority that you set is the same, right? So the priority you set on the generator side is the same priority that the supply side sees. So the priorities are, you've got to match those. But I don't know. Anyway, I think they should always have all your transformers the same priority to make it work. But anyway, all the transformers are going to auto balance one. So it'll add up all that's in the storage. It'll add up all the storage available. It'll come down here. There are going to be no consumers. So it'll skip this completely because it's just storage. It's just transformer. So storage count, the total in storage will be whatever. Total storage available will be whatever. So let's come down here. Total power used will be 0. Okay? Because total power offered will include power and storage. Right? There's no generators, so it will equal how much is in all of the transformers combined. You just add up all that power, and that's the total in storage. So that's the total power offered. This doesn't run. So total power offered at this point will equal total power in storage. So if we look, total power used, it will equal total in storage minus total offered, which will equal 0. 0. So 0, total power used, right, will be equal 0 power used will equal total power in gen, which is also 0. So this equals will make this in this specific case, well, that equal sign will make these jump in. So we take total storage used minus total power used, which again is 0, minus total power in generator, which is 0. Total storage used will equal 0. Okay, so I'm thinking there's a problem with this. So 0 total storage used, producer count, this won't go in there. This total power used is already 0. Okay, there's a problem. Total power used is 0. Okay, this is a problem. So it's total power used, extract power, total power used is 0. We're literally not extracting any power from storage nodes. We're not moving power at all. if total power used equals 0, break. No, there's no point in processing this further. Yeah, I could do this. Okay. I'm just trying to clean this up a little bit. Okay, so this is a problem. Total power used is 0. I don't want to make this an else if. I really, 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 really don't want to do that. Okay, so it's a special case if total power used equals 0, which means the total in storage minus the total offered are equal, or any one of these is equal. Power in gen minus power offered. You know, if the total power used equals 0, if, god dang it, total power used equals 0. See, this I'm so glad that I ran through this scenario. Right? This is the scenario that we started. And there probably could be other ones too, that this is the case. So, we did not use any power at all. Total power used, total power offered. And total power offered is greater than 0. We did not use power at all, but have some available. Okay. So we didn't use any, but we do have some. And this, I added this because in the case of a network that is, say, not finished, total power offered could be 0. If we didn't use any power, but we didn't have any power to offer, then, you know, it is what it is. Which means the network is just, maybe it's in the process of being built. Maybe you have a generator on it, but no transformer, no consumer, no machine. So it's just, there's no power used, but the total power offered is greater than 0. Or do we want to specifically look at a different case? So total power offered does include the total in storage or generator. These are the special cases that cause massive bugs if you don't account for them. Like massive bugs. And they're really hard to debug too. total power offered equals total power in generator plus total power in storage. Not 100% sure how to approach it. Because that use case, total power used equals 0, but total power in generators also equals 0. That means this is going to come in here. Total power used equals total power used, or total storage used. Power used is 0. Power in gen is 0. Well, total storage used equals 0, which means coming in here, total power used will equal 0. 0 minus 0 is 0. So this is going to bomb out. And it won't even throw this exception, but it also won't rearrange the storage, right? It's not going to rebalance the storages. Total power offered, yeah. So in this case, can you think of a scenario where it's not going to use any power? I can think of a few scenarios. The case of all the machines are shut down, right? You have a bunch of consumers. So you have 3 consumers. Let's say they're off. They're full and they're off, and you have a transformer. Well, total power used is going to equal 0. Total power offered is going to be greater than 0. But that doesn't necessarily mean they're all transformers. That just means they're basically shut down. So this is a really edge case, because in the case of this, 3 consumers, 1 storage, if we go through here, total power offered is 0, or no, total power offered equals the amount in storage, and we go through here again, total power used is 0, total power in generator is 0. We come through here, producer nodes, that doesn't go through. Storage nodes, that doesn't go through because total power used is 0. So we get through here, this is still 0. It bombs out of this without any howdy doody. It's just nothing happened, right? It just runs through this and literally nothing happens. But if everything is a transformer, or even if you have batteries, right? If you have batteries and transformers on a network, technically you only have storages. So it's literally only the case when storage nodes count is greater than 0, but producer nodes and consumer nodes are equal to 0, right? So if we wanted to simplify this, or at least explicitly cover this case, if consumer nodes.count 0 and producer nodes.count 0 and storage nodes.count is greater than 1. Okay. In this case, this is a very special case. We have no machines we have no generators, and we have more than one storage building. In this case, we want to rebalance the storage. Right? Now, not all storages will be able to hold the amount of power. If we just, let's say we just average, we say total in storage, right? Divided by the count of nodes. So if the total of storage is 1,000, then we divide that by 2, which is the number of nodes. Say it's a network with 2 transformers. Total of 1,000 divided by 2 is 500. Then we just set that equal, right? We set it equal to 500. We set each storage equal, which is the transformer. I don't think that would work. I don't think that would work. Because the transformers and the batteries are not going to have the same buffer size, right? You could have a battery. Let's say you have 3 storages on it. Let's say you have 2 transformers and a battery for buffer. And the battery has a 20,000 power buffer. And each transformer has 1,000 buffer. Well, in that case, even if they're all half full, you have 10,000 from the battery and 500 from each transformer, right? So that's 11,000. Well, if you divide that by 2, that's 5,500. Well, the transformers only hold 1,000. So now you're looking at, holy crap, how do you move that much power? Well, here's what we could do. We could take the amount that's in storage. Edge case of a network only having storage and or transformers. Edge case of a network only having storages and or transformers. Storage, transfer nodes. Okay. So, and it's going to be greater than 1. Because if there's just one node, there's just one storage, there's literally nowhere for the power to go. So we don't care if there's just one of them. So it's like a network with a battery on it. Like what? You're not gonna do anything with that because the battery there's nowhere to either deliver power to and there's nowhere to take power from. It's just one storage node, just like one transformer. It's like a network with just one storage on it is not going to do anything. I want to remove this if because else we're going to return. We don't even want to do any of this stuff. Literally, like, none of that. The first thing we're going to do here is sleep timer plus equals delta time. Which means just go to bed. Just sleep. Or no, we're gonna add this. We're gonna add delta time to the sleep timer. We'll figure that out. That'll come after the fact. Okay, so this only if there's more than one storage node in the network. Only run. If add to sleep timer. I'll add there are other situations where I'll add the sleep timer. Mainly total power used. In the case this doesn't get hit, because if consumer nodes that count as 0 and producer nodes that count as 0, then I know storage nodes have to exist because the network itself wouldn't exist. The network would not exist. So one of these things has to have nodes in it, otherwise there would be no network. So I don't need to check if storage nodes is greater than 0 because it has to be. It has to be greater than 0. You cannot have a network that is empty. If the network has no nodes, the network is deleted. Or will be deleted when I get around to doing that code. So only run if there's more than one storage node in the network. Okay. That means now the values here and here, total in storage and total storage available. What we want to do is just rebalance these. We just take total in storage and we rerun the system with total in storage. So in that case, if you have a battery and 2 transformers, the battery has 10,000 in it, transformers have 500 apiece, then you have 11,000 power. If I run through this and I give it the option of taking 11,000 power, well, each one of those transformers is going to take its share. Now the problem, obviously, is if the batteries run first, right? That's a priority problem. So the battery needs to have a lower priority than the transformers. Or numerically, it would be higher. So like the transformers would be 5, the battery you'd want to set to 6, which comes after 5, which is lower priority. So it would process the transformers first, and then the battery second, giving it whatever's left over. There's really no way efficiently to single out the transformers first without a mess of code and slowing the process way, 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 way down. So, again, I think I will default a battery priority to 6, and the transformers will just be default of 5, just like everything else. But the default values of all these priorities, I'm going to try to make, when I get around to making the blocks themselves, I'm going to try to make them have default priorities that the system actually works the way it should. So, for each electrical block entity in storage nodes, total in storage is what I need. So total in storage equals entity dot receive power total in storage false. Okay. Total in storage should equal 0 at this point. Okay, so all this does, if there's more than one node on this, all this does is grab all of the power that's in storages, because this is all if it's in this loop, there's only storages on it, which means batteries and transformers. So all this does is take the grand total of all of the power and distribute it into all the transformers. So it'll give a little bit of this, a little bit to this, a little bit to this, based on the received power. So the transformers can limit how much power they take per tick. So let's say you have an MV LV transformer. Now the buffer can hold like 1024. But let's say the per second rate is maybe I should add the delta time into this. Receive power. So you could limit it to how much power per second. So that the transformers themselves are limited to how much power they can move per second. And like an LV would be 512. So the absolute most that you could deliver to an LV transformer in a given second is 512 power. Now, if there's no use of that power on the other side, then the next second that rolls around, we'll add another 512 power, right? So depending on your draw, you could, that internal buffer, which is why I keep like a 2-second buffer, just to process any rounding errors. But this receive power and send power, so from here we return, right? We don't want to process anymore. We don't need to. There's no producers. There's no consumers. We've already balanced the power in the storage, and there you go. All of the transformers will even out themselves. Now, current power. So these values, current power, max power, current power, the implementation of these get routines, I could actually pass that value not as the current value, the current power. I could pass not the amount of power, but the amount of power per second that it's able to supply, which would limit the current power available to how much power in a second. And I could multiply that by delta time. So, do we want to pass delta time? That's something that I don't think I've ever seen a mod do for like Forge. I've looked at a couple different mods. But it would be nice to know total power offered is going to be a pretty big number. On the entity side of that, I will not know how much power or how much time the delta time is. I don't know. I don't know if there's a way. I don't know if there's a way to tell that on the other side, unless I track it myself in the end. Like I could just track what the time is, but the delta time is going to be a widely variable value. It's not going to be, 0.25 every single time. It's going to be a different number. So right now, I'm not going to worry about it. I may end up having to refactor the code to implement a limiter on power per second. Is that something? It'd be easier to do it now than later. I think if I look at the test machine, yeah, recipe power per second. A lot of this is, well, I haven't looked at this code in so long. I've been so enmeshed in the network and Catenary and then farming sim mods. Where is OnSim Tick? Recipe power per second times delta time equals power to apply. Recipes, if you look at, I think this is ubiquitous to mods. If you look at thermal expansion, if you look at immersive engineering, if you look at all these mods, the speed of the machine is independent of the recipe. The recipe, the cost, the thing that makes recipes slow or fast is the amount of power that the machine can apply to the recipe per tick or per second. So if you actually look at how recipes are built in like thermal expansion, recipes are built, yes, you have an input and an output, but the cost is power. And that's why the augmentation system for like thermal works so well, is all it does is modify the amount of power the machine can apply to the recipe. And that's what I'm modeling here, is the recipe, let's say iron, this is the test machine, it's hard-coded, but it takes iron ingots and makes iron plates, right? That recipe has a power per second cost, which is hard-coded, because a lot of this, these are just test things, so they're all hard-coded. But as you can see here, recipe power per second, I'm able to apply 32 power per second to the recipe. Now the recipe, if I find it in here somewhere, recipe okay, power to apply. Recipe power cost. I need to find that variable. Is that up here too? Recipe stuff. There it is. So, again, this is all hard coded. This will all eventually be run into its own object. You know, there'll be recipe objects for all the machines. But this, right, is the total amount of power that the recipe takes to finish. This is the amount of power per second the machine can apply to the recipe. I hope that makes sense, right? 302 power per second, 512 cost equals 16 seconds per craft. Very easy division. Which means in the future that if I start supporting augments, that you'll be able to upgrade a machine, well, then it could be doubled. Like I could make that 64 power per second, meaning it would take 8 seconds to craft. The recipe doesn't change. The power cost for the recipe doesn't change. It's the machine's power that applies different amounts of recipes. So that is how everything works. Now, the power per second, I think, if I have power stuff, yeah, this will be an interface. That is an interface. I just haven't applied yet. That's this interface here, right? So this, we look at this. Obviously, a lot of this is going to be familiar. So you can see the maximum power in here is 2048. Current power equals 0. It's just instantiating that value. Max power, current power, can receive, can extract, is powerful. Receive power, I don't think. So power needed is greater than or equal to power offered. Current power plus equals power offered. So we're because power needed is less than, we're adding it to it. In the case that it is greater than, we're just adding it and we're removing what we're using and then returning it. So extract power doesn't, it should never be called, but it's in the interface, so you have to include it. So I'm not seeing anything in here that is altering power per second. So the machine is capable of instantaneous filling. Let's say you have a machine on a network, right? Let's say you have a machine, it's just sitting there. And then you place a transformer. And then you hook the transformer up to the supply network, which immediately fills its buffer, right? Because it sees it's way down. You hook it up and it starts filling it because it's averaging out the power, so it fills the buffer. Now you connect the other side of the transformer up to the machine. So there's 1024 power in the transformer, and there's 2048 power available in the machine, or whatever the machine has. Again, those values are all arbitrary. Well, immediately, the next update tick, it's going to take that transformer power and dump it all into the machine. So all 1024 power is going to dump into the machine, and then it'll be balancing, right? The machine will slowly fill up with the power being delivered and balanced by the transformer. So in my mind, that's how I'm looking at all of this, trying to figure all this out. Converting the test machine and the test generator over to actually use this infrastructure is going to be a really intense process, because there's a lot of code, there's a lot of XML, a lot of JSON stuff going on behind the scenes that largely is untested. And so getting those machines over, because these entity class, right? So BE test machine is the entity class. Well, instead of, if I go to block entity, BE test machine, you can see it is block entity openable container. Well, that's not right. I need to implement the interface I block entity. So you can just take this, put a comma, and do I electrical block entity, which now is like, holy cow, here's a whole bunch more stuff that you have to now supply and support. But, and there's a couple other ones. There is, I think it is, no, that's the block. So the block BE test machine, right, is just block. Nope, that's not going to be right. You're going to need wired block. Wired block is part of the block, but it has I wire anchor, right? So in order to tell the game that a wire can be attached to this pot, you need this interface. And this interface comes with all of these things to load, right? And so rather than inherit from block in your test machine, not the entity, block test machine. Instead of doing block, you make it wired block. And now you inherit that, and all of this stuff is automatically done for you. You don't have to copy and paste any of this. It's already done for you. That's, yeah, to do all of the things. Yeah, there's a ton of code in here that's not done yet. Like, there's a lot of stuff in here. On block removed, The reason why there's a to-do on this, when you remove a wired block and there's wire connection to it, you need to let the system know that this block was removed, that this wire was disconnected, and I haven't done any of that code yet. So again, there's still a ton of code that's needed in here, but as you can get the drift. I think, as far as the electrical network update routine, I think it's done. I'm just going to leave this here just because I'm too afraid to remove it just in case I need it. But I mean, as far as testability goes, it's in a place already that I can test it, and I can put different networks together, and I can test each one of those. Just build different networks and see how the code runs out and see if it actually works. But again, I think this is overall done, and it's relatively efficient. It may not look like it. It's 100 lines long or so. 164, 293. So it's about 130 lines. A lot of that is going to be comments, of course, and braces. But how many times, here's the important bit. How many times do we iterate through these lists, right? So producer nodes here is once. So at most you're going to have 1, 2, 3, 4, 5, 3, 4, 5, 4, 5. So at the absolute most, you will iterate through a list 5 times. That is worst case scenario. That is in a case that you have producers, consumers, storages, all on one network, which is 100% possible. You have all 3 types on one network, and they have to iterate through in whatever combination cascades through here, right? So you could have any one of these situations in these if-else's, but actually iterating through them, you're only doing, this block or this block. You're not doing both. So 5 iterations through a list is all we're doing. That's the maximum, which is glorious, because that is pretty darn efficient. And we have a special case if we don't have any consumers or producers, and we have storages. We have more than one storage, right? If that special case is just rebalancing the power. That's all that's doing. Is taking total power and just redistributing it. Which could, fill the smaller transformers and give less to the big transformer. But also that big transformer is, should be getting supplied on the other side of the network. Like a different network is supplying it, and it's auto balancing on the other network. 2 networks independent of one another. They're all using they're both being ticked, but they're not being ticked at the same time. This is not a multi-threaded situation. So you're not getting a race routine. You're not getting a deadlock or an infinite race routine, right? It's this network is ticking, then this network, then this network, then this network. It's not trying to tick all of the networks all at once, which would be a nightmare of trying to lock and trying to manage the multi-threaded aspect of it. So we're not doing that. Maybe if I present this code to Tyrone, he could pick it up and improve it in some way. I'm sure somebody of that caliber, or some other expert in C# or who had been programming for many years, could come up with a more efficient or a better way of handling all of this stuff. But I just want to get the damn thing to work so I can get onto the fun stuff, is making all the machines, all the recipes, all that kind of stuff. That's what I want. But I got to get through this first. So yeah, I think we have a function that is at least able to do what we want. There might be an edge case. There might be something that I haven't accounted for. But anyway, I think we can still like build solution. Yep, one succeeded. Look at that. It still compiles, that's a good sign. And remember, I've already converted this project up to the new .NET 7. So this whole project I had to convert last week with the new .NET 7 that the game is now moved to. So yeah, the game is already, or the mod is already moved to the new version of .NET for the game. So I don't have to do any of that. I don't have to do any of that. So that's so good. Yeah, and the whole cheat power thing, again, yeah, I could easily create a routine for the electrical, the electrical network manager, right? So you take the mod. This is how you do this. Electrical network manager. You take the electrical network mod. This is where you would define the command, and you pick up whether or not they run the command. But unfortunately, this is a server-only side mod, right? It's not running on the client. So I can't really add anything client. I would have to, yeah. I don't really want to have the client running all this code too, because it would just slow them down. It's more efficient for just the server to manage all of this. But I could make this listen for a command and then put the command somewhere else. Like, yeah, I could put it somewhere else. And just, when the command is said, I could just pick up this mod system, and then send the command that way, and it would just cascade it down. Pick up the network manager, right? So electrical network manager. Then I would just have this call, and it would just iterate through the networks, iterate through all the nodes, and it would just max out the power. Just one command, max all the power, and Bob's your uncle. I'm not really instituting very many cheats into this system. Because, that's just, those are like edge cases. I don't really need cheats. But a cheat would be it would be a lot easier to do a generator that just provides infinite power. Right? That would be a cheat. Generator, you just plop it down and boom, it's infinite power. It just generates power from nothing. That's a lot easier to implement than trying to run commands. Just no way would I do that. But as far as testing and stuff goes, sure, you could add a cheat block for both consumption and production of power. Just an infinite sink of power. That'd be easy to do. All right. Well, I'm honestly happy that we are able to get through all of this. And again, if anybody is watching this days or weeks or months down the road, feel free to ask questions or comment, or if you followed this whole thing and you still find a problem, or you have figured out an edge case that doesn't quite work, and you've watched and how this cascades, and I've kind of run through it many times now. So eventually all this code is going to be up on my GitHub. It's not yet. I should, but not quite yet. But yeah, this should work. But anyway, I want to thank you all for coming by today. This is going to be it for the stream. I just wanted to do some development and show you I'm still working on the mod. So good times. But yeah, that's going to do it for today. I thank you all for coming by, and I will see you next time. Oh, Saturday, by the way. Saturdays are next. I want to say that. Wednesdays and Saturdays is when I stream.